any questions? Time to start, I guess. So thank you for being here. Oh, sorry, despite some competition. What's happening? Okay. Hello, everybody. Thanks for being here. I am Luca Ceresoli. I am an embedded Linux engineer at Bootlin. We do development on embedded Linux, especially Linux kernel device drivers, build systems, bootloaders, firmwares, and so on. We are very open source oriented, and we also do trainings. And I am mostly doing kernel device driver development. And recently I mainlined a audio codec driver, which was an obligation and an opportunity to learn about DAPM, which is the subject of this talk. And I live in Bergamo, in the north of Italy. So, let me first introduce the topic with a bit of background, starting from the big picture to what DAPM actually is. So you probably know that ALSA is the Advanced Linux Sound Architecture, so it's the audio subsystem within the Linux kernel. It exists since more than 20 years now, so it's very clearly its API are working well because they are still in use. And so ALSA, when it was introduced, it was in the era of Sound Blaster and similar. So the abstraction of a sound card was conceptually pretty simple. So one sound card is one device, which is a data bus to connect it to the CPU, the memory, the central processing, and audio on the other side. And as such, it was modeled in the Linux kernel. So it is one device, which has one driver. It exposes to user space an interface, which is providing playback streams, capture streams, and key controls, which allow to modify various settings, such as gains, muting, selecting path for muxes, and so on. So this works pretty well for this kind of sound cards, but it doesn't easily allow to reuse components. So when sound cards start reusing some of the components from another model, but not all, it was becoming a bit complicated to reuse the code. And this was even more relevant for embedded systems, where it is totally normal to mix and match components. So you can use the same codec with a different system on chip, or the same system on chip with a different codec, and then maybe you add an amplifier. So all these components can be mixed and matched. And so the model was not perfect for this aspect. So ASOC, ALSA for system on chip, was added a few years later. The idea is that a sound card is not anymore a single component. It is a group of multiple components, and each of them has a device driver, a separate device driver, and the sound card itself has another driver which glues together them. But the user space API is not different, so you still use the sound card in the same way with the same tools. This works very well. And there is, however, a specific need in sound components, which usually in the audio world, especially codecs, they allow to have a very flexible routing. So you can select the path of the analog sound in very sophisticated ways. You can see in the picture just a piece of, a small part of the block diagram for a codec. As you can see, for each decimeter can receive its input either from a digital microphone or from an analog microphone. And depending on the path you want to use, different components are needed. For example, the sigma delta and the PGA are not needed if you use the digital microphone. So for power efficiency, it's better to turn off whatever is not used in the path of the sound. This is, however, not very easy to implement in code, or not necessarily difficult, but difficult to maintain because there are lots of possible combinations. So either you have a driver that enables everything, which is simple but consumes too much power, more than needed, or you have a complex driver with lots of ifs and else, which it's a bit tricky to maintain. For this reason, ASOC from the beginning contains DAPM, or DAPM, which is the Dynamic Audio Power Management. It is the subcomponent in ASOC handling this. So there is already runtime power management in Linux, which works very well, but it's not suitable for this because it works at the device level at a higher granularity. And for sound, it's a bit different because you can have hundreds of components in the same codec very small components of the audio path that can be enabled or disabled. So DAPM is an independent power management mechanism. It is independent and can coexist, and it does coexist with runtime VM. It is totally transparent to user space, so you don't control DAPM from user space. It just works automatically when you enable and disable the features and you change your routing. So every element in DAPM is described as a big graph, a big connected graph. So each item in the graph is called a widget, and it represents an item in the hardware that can be enabled or disabled, turned on or off. And each connection between two widgets is called a route. And DAPM automatically enables the components that are on the active routes. Look at the two pictures at the bottom. If you want to capture from an analog input, you need to enable the IDC. If you capture from a digital microphone, you don't. So DAPM will automatically enable and disable the IDC. You don't have to write any code or do anything in user space to enable and disable that. So, and also this works thanks to the K controls. So the K controls, which are user exposed, are controlling the path, and some components, I'm sorry, I hear my voice back. It's 1, 2, 3, yeah, better now, thank you. So each widget can have a K control controlling it, and this is especially for the widgets that control the path of the sound. So muxes, demuxes, mixers, switches. And DAPM will take this into account to understand what is the active route. So the DAPM graph spans the whole sound card. So each component, you see the codec and the amplifier in the example picture, implements its own widgets and their internal routes, internal to the component. And then the sound card implements the widgets which are outside of various components, such as the internal speaker or the jack detection and so on. And it connects those together with the components, and it also connects the widgets of two different components to each other. So it glues together everything. There is documentation for DAPM. It's in the kernel documentation, so it's there since a long time. However, when trying to understand DAPM, I found especially the introductory parts not complete enough, at least for my understanding, and so I proposed a patch series, which I sent a few days ago to improve the documentation. So it has better introductory sections to introduce the topic. I can also recommend about DAPM these two talks, both by Lars Petter Clausen. The first is a general overview of ALSA and its history. It also covers DAPM a bit. The second is DAPM specific. Unfortunately, there is no video recording available, but the slides are useful anyway. So there are lots of pictures, they are pretty clear, so you can get some more understanding of DAPM from them. So now let's get into the technical details, and let's talk about widgets. So there are various categories of widgets. Let's have a look at the main ones. So endpoint widgets are widgets where the sound originates from or terminates to. So they are called source and sink widgets. Some of these are the ADC or DAC, which is where the analog sounds become digital or the other way around. And so this corresponds to waveforms that will be stored in memory or get read from memory. And the other type is the analog side towards the outer world, so a speaker, line out, microphone, and so on. Those are the ones that will get enabled when you start a stream. And then there are pass-through widgets, so widgets that the sound needs to go through, to go from the source to the sink. Those are sound modifiers, so PGA, which means a gain, basically, so an amplifier or a gain, or effects, and routing widgets, mixer, muxer, demuxers, and switches, which can modify the path of the sound. And finally, supply widgets, which are not manipulating audio itself, but they are providing something to the other widgets, typically a clock or current or voltage. So let's see what DAPM actually does when you are using it at runtime. Basically, whenever you change the routing in any way by modifying a key control or by starting and stopping a stream, DAPM goes through two main steps. The first is to determine the new power state for the next state. So it starts by considering active any source and sink widget where the sound needs to go through. And then this is valid on the two ends of the sound, or the sound stream. And so those are powered only if they are active and they have a route to an endpoint in the opposite side of the graph, which is also active. So if you enable the speaker but there is no PCM, it doesn't make sense to enable it. And then it goes through the path to find the route from the source to the sink, and then it considers active and it turns on all the widgets along the path. So this will change whenever you change a key control that modifies the routing. And so this is computed by DAPM automatically. You don't have to do anything. It's done internally. And last thing is every supply widget that has a route to an active widget will be also powered on. So this is conceptually simple. It is walking around the graph, but it's actually much more tricky. So the algorithm takes into account many aspects. One of the main goals of DAPM is to reduce to a minimum pops and clicks when you start, stop stream, you change routing or the mixing and so on. So there is a specific sequence to turn on and a specific sequence to turn off depending on the widget type. But when writing the device driver, you normally don't need to take into account all of this because it's in the core. The second step of DAPM after computing the new state is to compare the previous, so the current and the following state, power down all the newly disabled widgets, then apply routing changes and power up all the newly enabled widgets. This is, again, to minimize pops and clicks. Okay, so when you need to write a device driver for a codec or any other component that has a flexible routing in it, you need to know about a couple things. So the first is the structure, a SoundSock DAPM widget, which is representing a single widget. It has a lot of fields. You can see here only the most relevant ones, especially those in this area here. You have a register offset of the register where you have the beat or the bits to enable the given widget, and then a shift, a mask, and other information to actually be able to modify the specific beat or bits for that control. You have a name, a stream name, and other aspects. And you also have a function pointer. So in case the DAPM core is not clever enough to handle complicated actions you need for your widget, you can just provide a function pointer, and in your function you implement whatever logic. For example, you need to enable a GPIO to enable an amplifier. Well, that's not supported by DAPM. You can add your own function handler. However, now that you know about the structures, never use it because it's pretty complicated to fill all the fields correctly. There are many macros, a lot of macros in the sockdapm.h include file that you can use to fill the structure for each type of widget. There are a few examples in the picture. The first is an input widget, so it's just an input pin. The second is a supply. It has a name, a register, an offset, and so on. So DAPM will know which bit to set in which register. And you can look also at the second last one, which is actually a MUX. And so it also has a key control associated to it, which is where you can control actually the path you want to assign. You might notice that there is a register offset in here, but there is no base to the address space of your device. This works thanks to regmap. Regmap is a library component within the kernel, which originates from ASOC, but it's now generic to all the kernel, and it's used also outside of audio. So regmap is an abstraction to represent your a register that can be modified, and you can use a regmap without needing to explicitly tell the bus it is working on. This is important for many audio codecs which can be controlled either over I2C or via SPI. And so for this reason, regmap allows to just call regmap, set register, and so on, without having to differentiate your code for the two buses. You just do that at initialization time, and regmap internally knows how to access the bus. It has many more features. Regmap is worth a presentation on its own, but it's out of the task of the topic here. So when you write an audio driver in Linux, regmap is close to mandatory. So it's really super recommended because it's handy, but also because it's something that is internally handled. So when you add a new component, so when you implement a codec driver, an amplifier driver, whatever, you call soundsock add component to add it to the kernel, and then it will populate a regmap automatically for you, unless you do it already. And so ALSA is already able to access your register. So it's very easy and free to use regmap in audio. Next thing you have to define is, of course, the routes, the connections between the widgets. And for this, there is another structure, soundsock.pem route. This is much simpler. It has mainly three fields, which are the sink, so the destination, the endpoint where the sound goes to, the source, which is where the sounds come from, and optionally a control in case you have a key control. You may notice that these are strings and not pointers to structures. A lot of things in ALSA are string-based, so you don't write pointers to object. You write the string name of another object, and then the core will do string matching to find it. So it's string matching everywhere in ALSA. For example, to define your routes, you can, the typical way to do it is to write an array of these structures, and each element in the array has always the source and the sink, and also the control if applicable for a mixer or a MUX in this example. And so you may notice that the direction is reversed, so from right to left. In the first line, for example, the analog in 0 goes to PGA 0. So I find it a bit counterintuitive, but once you know it, it's okay. Okay, so for the mixer here, you have an idea of how to implement them. So you have the text here, which is what will appear, for example, in ALSA Mixer, if you use that to select your routes. And this is how you pass the information to a route about the key control. Okay, so finally, when you define those two structures, it's very easy to add them to your sound component driver, a codec, for example. In this codec here, for example, we have, as you can see in the soundsock component driver structure, you just have to fill the DAPM widgets and DAPM routes pointers pointing to your array and the number of elements they have, and the core will do the rest. So it will take them, connect all the routes, do all the string matching, and so on. But there are cases where this is not enough. For example, if you have a driver that supports multiple similar versions of different codecs, so different revisions of the codec have different features, so you need to detect the model at probe time and then configure the graph for the specific model. In that case, you can create more arrays of widgets and routes, and then based on whatever logic, the model, the revision, whatever, you can call soundsock.pem new controls and soundsock.pem add routes to add them at probe time. So your graph will be specific to the model you are implementing. And finally, you need to connect your graph to the DAI, which is the digital audio interface. So basically the SPI bus or AC97 bus, whatever bus connects to your chip on the digital domain, to your system on chip. To do this, well, you have these techniques. So you specify let's start from the bottom. When you define the DAI driver, so for example, your I2S interface, it has a name and then a playback stream, which has a stream name, hi-fi playback in this case, and the same for capture stream. So this string can be used here when you declare a DAC or an ADC component, widget. And the second parameter is the name of the stream, which will be associated by the core to the stream itself. And this is done again based on string matching. You may notice that the string is not the same, so hi-fi playback, but here we have left or right hi-fi playback. So it's actually substring matching. The stream name must be a substring of your stream name in the widget. So something to be careful about. Do copy-paste and don't type twice the same string because it's too easy to get a small typo and nothing will work. Okay, so this is basically all you need to implement DAPM in your code. So conceptually, not much to do. Maybe many lines because you have many widgets, but this is all you need for using DAPM in your codec or whatever driver. Now, let's have a look at how you can inspect what DAPM is doing at runtime to know the status, what's happening, which paths are enabled, and so on. So, well, as I said, DAPM is internal to the core. It works internally. It's not exposed to user space. You never need to ask DAPM to do something. You enable your streams, you change your mixing, muxing, routing, and it will do whatever is needed. So it just does what you need. So it works. You don't need to inspect it. So no problem. Well, unless you want to learn how it works, or maybe you need to debug something, of course. So there are actually tools to observe the state of DAPM. The core tool is debugfs. So DAPM exposes each widget as a file in debugfs. So in syskernel debug, or whatever you mount debugfs, ASOC subdir, and then there is a subdir with the card name, which has a DAPM subdir with one file per each widget that is at the card level, so the external connectors and so on, usually not many. And then there is another subdirectory for each component, which has a DAPM subdirectory with all the widgets inside the given component. The content of those files looks like in this code snippet. It's a few lines. You can see the state on or off in the first line, and also information about the registers. It will be setting, so you can check if it's correct according to the datasheet, and the stream name, whether it's active or not, and then the routes. So you can have 0 to n lines of output and 0 to n lines of input. For example, a mixer has multiple inputs normally. In this case, there is only one input and one output, and you can see the name of the widget that is on the other side of the link. When starting using this for my development, I noticed a problem that the widget name can be ambiguous. For example, in this sound card here, the STM32 whatever, there are two widgets called capture because they are into different components. So the components have completely independent drivers. It's totally possible that you have a name collision. So I proposed a patch adding also the component name on the same line, so it becomes non-ambiguous. And also, in this same series, there is another line with the widget type, so you know that this is an ADC widget, which you might guess from the name, but it's not necessarily the case for all the cases. And also, this is parsable by software tools. And about software tools, there is one which is called visDAPM. It is a very simple shell script. It's about 50 lines of code. It was written by Dimitris Papastamos at Wolfson Micro. It is able to generate a graph, a picture with a graph of the DAPM state as a PNG picture. It is based on the dot tool in GraphViz to do the graphic stuff. However, the repository disappeared from the Wolfson Micro website, but there are Git forks around. To use it, you have to call visDAPM, and then the directory the DAPM directory for the component you want to inspect, and then the output file name. The result looks like this. So it is representing the DAPM state of a card. And you can see the green circles mean the widget is active. So it was very useful when I started using DAPM to understand what I was writing in the code. I like tools to visualize what's going on. And however, I also found a few issues with the script. It needed a few tweaks to work on busybox shell on my target and a few other stuff. So it's a very simple script. You need to adapt it. So I started to do some improvement to fix the issues and add a little more features. But soon I realized that basically I was going to rewrite the whole script to add even more features. And so I came up with a new tool, which is called DAPM Graph, which I proposed in the same series I already mentioned a few slides ago. It is inspired by VizDAPM. It is also using Dot from GraphViz to generate graphics. It is also a self-contained shell script, but it is more, let's say, embedded developers friendly. So it works on busybox shell, and it has also a remote mode. So when you call it, normally you call DAPM Graph the output file, which can be also a different format than PNG, and then the card name. But if you also pass -r, it will connect over SSH to a target, and then grab this DAPM status from there, bring it to your machine, and process it locally, so it's faster, and it doesn't need graph feeds or whatever on the target. And it has also a few more features, and it also has a nice command line help so with all the various available flags, and the result looks like this. So it is showing all the components in the graph, not only one, and also the connection between the two components, between different components, as you can see in this area of the graph here. And so it has been submitted. I hope it will be accepted, so it will be available in the kernel source tree. And well, last thing I want to mention is that if you need to go even lower in the backend, lower level, to understand what's going on in the code, which is something I did to understand better what DAPM does, the sequence of operations, I've been using ftrace, which is very nice for this kind of thing. And well, in my case, I use trace command because I'm lazy. You can see the command line there, but you can use normal ftrace, whatever. There are events exposed by ASOC. So you can see here, or you can just pass ASOC and it's the same. And I also added, the functions from my codec to see when my codec driver was being called, and I used the function graph tracer to play a file. So I could see that the first thing that happens is that your hardware parameters for your codec is called to set the format and NDNS, whatever. And then DAPM Power Widgets does all the DAPM work. It emits some ftrace events to tell when it started, when it's finished. And the first thing it does is it computes the new state in SoundSock DAPM widget power to fill the new route, to see what needs to be turned on off. And then it calls SoundSock DAPM path to propagate the state through the various widgets. And when it's finished walking the graph, it prints some statistics, and then it starts calling all of your widgets to modify all the registers. For this, it emits these ftrace events. Here, a SoundSock bias level start and done for each component. These are called in separate K threads. That means they will be interleaved in our ftrace output, not very readable. So I've used max CPUs equals 1 on the kernel command line, so that becomes linear and more easy to understand. Also if you have an event associated to a widget, you will also see the SoundSock DAPM widget event start and done before and after it's calling your event callback. And at the end of all of this, audio streaming starts. And at the end of audio streaming, everything is rolled back. So basically the same sequence in reverse. It's worth pointing out that you can also have ftrace events for regmap. So you can also see very granularly when each register is modified. And so you get even more low-level information. And that's all. So I'd like to thank ASOC maintainer Mark Brown for reviewing my slides and proposing improvements. And that's also, any questions? everybody's shocked. Okay. Yep. Yep. Maybe. Right. Yeah.
Is there obviously the current configuration is all just source code based, so every board has a giant array of everything. Is there work in progress or thoughts on moving this to like more of a device tree kind of configuration mechanism? I know that the Intel folks have this HTL CPI table that has a lot of this information. I was just kind of wondering if there are migration strategies for board level configuration that was not, a
Not sure I completely get the question. So you said the card is creating all the configuration, and the question is, what can be moved to device tree?
Yeah, right. Exactly. Or what are those?
Actually, well, it's already something you can put in device tree in the sense that, so the old way to implement an ASOC sound card was to implement your own driver, which populates the various components and glues together them. But nowadays, it's rarely needed because usually you can use one of these standard sound cards. They are called simple sound card, simple graph card, and similar. Maybe I can show you something. I don't know. Where is it? No, I cannot show anything. So, but anyway, there are those drivers which are generic sound cards, basically, and you define in device tree what you can do with them. So basically you define in device tree you have the codec under maybe an I2C bus or whatever, and your DAI, so I2S controller or similar, and then you just add a new node in. Well, but this has to work somehow. So.
There is also a theming topology where you write your topology in a text format in user space and compile it. You can load it at runtime. Yeah, but that's horrible. I mean, I don't know which one is worse.
It seems like there have been a couple of attempts to solve this.
Yeah, Intel does with the topology, and the rest of us with this.
Yeah, I'm just like, yeah, exactly. Well, the devices themselves obviously are awesome, and the topology information about what connects to what seems to be very ad hoc.
So I think this is the one I showed in the slides, and so the yeah, it's here I think. We can get it. So in the root node, you have this sound node, which is your card. So in an embedded system, a card is not a physical object. It comes out of the interconnection of multiple components. So in this case, you're using the audio graph card. It's a sound card driver, which is generic. And you need to point it to your DAI, and so which will in turn be connected to your codec. And you have the routing here, so you can connect the various widgets. So this is basically how it glues together things. So it's generic, and it works, I think, for 99% of the cases. There are actually multiple, there are 3 options: audio, simple audio card, or something like that, audio graph card, which is used here, and also audio graph card 2. I don't know what it changes, what is the difference, but it's pretty new. Okay, yeah. And so at the codec level to compose pieces together. Well,
security describing the integration of the different hardware components, but how the work is handled. How the work is handled is the job of the driver. The device is not to describe anything or details of what's inside the codec. So that's why you've got kind of a two-level.
You want the mic? On the microphone?
You describe in the drivers how the codec is working, how your amplifier is working, the internal widgets that they have. And then in device, you describe on that particular board, this is like how my codec is connected to my amplifier, how this is connected to the DI on the SoC side, that kind of stuff. So that's why. Go ahead.
That makes sense because the codec is static. There's no configuration that you would do as a user. So what that part of it is, like that glue.
Correct. Yep.
So basically, if you look like at this picture, if you look at the schematics of your product, a box in the schematics equals one thing in one object in the device tree, one node in the device tree, which is a device, which has its compatible string, which is the product name and vendor name, and everything else is implemented in the code in C. So that's the abstraction with device tree. Okay, other questions? No? Okay, so thank you. Enjoy the rest of the conference.
Great job. Great job.
Okay.
Oh, yeah, there's a button. I was looking for the button.
Hello, hello. Can you guys hear me? Yeah, cool. I think it's 9:55. We'll get started. Thank you for joining. This talk is about my experience at Memfault integrating Rust on embedded Linux. I'll share basically everything I wish I had known when we started, and hopefully there will be something for everyone in the room, whether you're just considering Rust or you've already adopted Rust and you're already using it a lot. So we will go and try adopt Rust together and unwrap a few lessons. Just a word of context. I won't talk too much about what I do for work, but Memfault does an agent that runs on Linux. So my talk is very much focused on user space Linux. We collect metrics from embedded devices, capture core dumps when they're generated by the kernel, do some parsing of the core dumps, capture logs from the system, store all of that locally on the machine, and then at regular interval, we upload the data if the owner of the device has requested that the data be uploaded. So we're very much a Datadog or New Relic for embedded devices. And so that just gives you a little bit of context on where my experience with Rust is coming from. I've been writing Rust in a professional capacity for only 18 months, so I definitely do not claim to be an expert. But my company, working with a lot of embedded companies, people who ship real product in the world, our code ends up on a lot of devices really fast and also on very different devices. So hopefully a few of the things I've learned will again help you. So when we were considering Rust, we had a few questions. And so I've broken down this talk into three parts. And first, we'll talk about toolchain and compiler. Specifically, we'll talk about is Rust going to work on my platform? And then is Rust going to work on my OS? So I'll talk a little bit about our experience with Yocto. I think most people shipping embedded software are using Yocto. We'll share what I've learned there. Then we'll talk about writing code, how we learned about writing good Rust code, how we got better at writing Rust code, best practices we've used and we're still using today. And then we'll talk about optimization. I think something that's very characteristic of embedded engineers is we care a lot about optimizing, especially size. And it was a big question mark for us when we started using Rust. So I'll share, again, some of the things we've learned here. A little bit about me, so you know where that information is coming from. My name is Thomas Sarandi, Thomas. I'm from France originally. You can find me on GitHub and X and Twitter at Sarfata. My experience is mostly building Linux products. I've done that for over 20 years now, shipping Linux appliances, a lot of different hardware-related job. In the US, I've worked for Pebble and Fitbit, shipping smartwatches. So if you guys are familiar with that, always love to talk with ex-Pebble fans. And then I went on to do more software engineering management and finally came back to a more technical role. Today, I'm the field CTO at Memfault. And so again, what we do is that we help embedded companies ship better firmware, very simplified. Okay, so let's get into it. First, we need tools. And the first question we have is Rust going to run on my platform? Is it going to run on my board? And so if you're at the stage where you're not sure, I would recommend just running rustc print target list, and that will tell you, all the supported target of the compiler in the 177, I believe, when I did that. I had 237 supported target. If you zoom on Linux, you have 75 targets. My point here is that although there are some platforms that are not supported by the Rust compiler, they're pretty esoteric. I generally tell our customer that if it runs Linux, our software is gonna run on it. Memfault is gonna run on it, and Rust is gonna run on it. I have yet to find a situation where that's not true. So, if it runs Linux, it's gonna run Rust, and if it doesn't, you probably already know that you have a pretty weird platform. So after yesterday's talk from, who was in the talk with Fabian from Linaro? he mentioned that the Linux kernel actually supports more platform than the Rust compiler, which is something I did not know. And so I asked ChatGPT this morning to give me the list of platforms that are supported by GCC and that are not supported by Clang and LVM and therefore Rust. And so that gives you an idea of which platform are not supported. They're really weird platforms that I've never seen in the real world. And I don't think anyone is shipping new hardware with them. So most likely Rust is going to work for you. First check mark. The second question we had is, how do I cross-compile Rust code for my target? When we're all working from our x86 or ARM desktop, we're trying to ship code on different architecture. Can I do this easily from my computer? And so the answer is yes, at first. So the first thing you're going to do is run cargo build -- target, the name of the target, so for a Raspberry Pi ARM v7. And that is going to compile your code, but you might run into issue when you're trying to link the code at the end of the compilation process because you need all the cross-compilation tool installed on your computer. So you can, of course, install them, but it's a little complicated, and when you're working in a team with other people, it might actually be difficult to have a really reproducible build environment. So at this point, you might be thinking, that's not a problem. I've done that before. I use Docker all the time. I'm just going to build Docker container. You'd be going right in the right direction. And I have great news for you. There is an amazing tool in Rust called CrossRS that does all this for you. So Cross is basically a wrapper around Cargo, which will, depending on which architecture you're building for, will start a Docker container with all the dependencies you need to build for this architecture, to cross-build for this architecture. It will build your code, and then from your perspective as a developer typing cross-build, it looks exactly like running Cargo, but it runs it in a Docker container, and at the end, you have your binary that's going to work on your target architecture. So you just take that, SCP it on the target machine, and it just works. It's really, really, really cool and really easy. And it's also pretty easy to extend. So one thing that you might run into is that you need some system library. You want libSSL. We'll talk about why you might want libSSL later in the talk, but you might want libSSL, or you might want some other C or C++ library that you guys have built and that you need in the build process. And so it's pretty easy to also add instructions in the Docker container build process to customize the Docker container used for the build and get it to have the right build environment. And so with that, we have a reproducible build environment. We know how to build binary for our targets, where we can really get started. Next question is, how do I ship my code to my user? And so, for us, this means mostly Yocto. We have customer using other build system for images. I'm not as much of an expert, so I won't talk too much about them. But I'll focus on Yocto today. And so there are two solutions to build Rust code on Yocto. The first one is called Meta Rust, and it's a layer that was started in 2014 by Cody Schaefer. It was merged in Open Embedded at the time of Yocto 3.4 Honister, so it's official inside Yocto since Honister. The way it works is that it provides a cargo class, and so you make a new recipe, you inherit the cargo class, you point to your cargo.toml file, and just like you would point to a C repository on Git, and it will build your Rust project as you're building your recipe, and include the binary in the target image, just like basically any Yocto recipe. So it's pretty easy. There are a few things that are important to understand about this approach. What Meta Rust does is that it builds the Rust compiler from source when you're building the project. So this is very much in the ethos of the Yocto project that we want to build everything from source. The interesting tidbit here is that the Rust compiler builds from the Rust compiler. So you can't really build everything from source. You have to start from an existing Rust compiler. So they download a snapshot of a Rust compiler for your architecture, and they use that to build a new Rust compiler, which is then used to build your project. And so It works, but it's a little slow, and that's one of the biggest complaints about this approach is that it will slow down your build. And if you're like us and you ship code to customers who integrate it inside their product, they don't really want you to slow down their build by, 20 minutes. That's not really a cool thing to do to your neighbor. And then the other thing that's a little specific about this approach is that they require you to list all the dependencies that you use. So when you're building a Rust project and you're using Cargo, Cargo will generate the cargo.log file, which, if you're familiar with NPM, you have a good idea of what that does. And with MetaRust, you take that cargo.log file, you transform that into a list of dependencies with git hash and a checksum of the dependency so that in the fetch phase of the Yocto build, it can download all the dependency, make sure they're all exactly what they pretend to be, and then it will build from that without network access in the compilation phase. So that works, but again, that means when you're updating your dependency, you need to update your recipe, a little annoying. And then finally, because it's official and part of Yocto, each version of Yocto now has a version of Rust associated to it. So I've listed the version of Rust up there. And it's very typical for us to still see customers that are using Dunfall, which was just end of life. And so Dunfall is not really supported by MetaRust. But I think we're going to be seeing Kirkstone for a long time, and if you want to be stuck on 159, Rust 159 forever, that's not great. We often want to update the compiler, get a newer version. And so if you find yourself in a situation where you can do is that MetaRust still exists outside of OpenEmbedded, and so you can override the MetaRust inside OpenEmbedded with MetaRust, and then this way you get a newer version of MetaRust with still the same philosophy and same approach I just described. The other solution to build Rust code in Yocto, and you can probably tell now that this is the one we have chosen and we prefer, is to use MetaRustBin, which is a project of the Rust Embedded Working Group. This one uses precompiled binaries for Rust-C, Cargo, and the standard Rust library. And so that significantly reduces your build time. It's compatible with all versions of Rust since Dunfall. Because it's distributed as a separate layer, it's also always providing the most recent version of Rust if you want it. And it uses, the important point here is that it uses a different class name, which is cargo bin. And so you can actually have a project which uses some MetaRust for some recipe and MetaRustBin for some other recipe, which is really useful because MetaRust is now a hard dependency for some of the Python packages. There are some crypto packages in Poky that depend on MetaRust. And so you can't actually completely override MetaRust. And so 6 months ago, this was a problem because the only way to use MetaRustBin was to override the built-in MetaRust, and then some other packages would not compile. We've solved that now, and you can use MetaRustBin in parallel with MetaRust. At which point you have 2 Rust compiler, but at least you have a build that's exactly what you want. So as a summary, you have 2 solutions which are both supported by reputable sources. One is supported by the Yocto, it's official as part of OpenOE. The other one is supported by the Rust Embedded Working Group, which is an official working group of the language. So both are pretty solid. They both have their pros and cons. You might have specific requirement for your project, but I would say building Rust project in Yocto is pretty mature at this point, and has been working for over 10 years now. So it's definitely not a problem to ship Rust code in Yocto. So I'll give us another check mark. And at the bottom here, unfortunately, you can't really see it. But there's also a blog article I did on interrupt.memful.com a few months ago, which went into more details in comparing the 2 approaches. So if you want to look into that, it's in the slide, and it's on interrupt.memful.com. So once we have all of that tooling, sorry for all the complicated setup here, but now we're ready. We can write code, And so first question is, how do I adopt Rust into my project? And so one thing we considered just rewriting everything to Rust or doing it progressively. We chose to rust the C code one file at a time, and retrospectively, we think this was a really, really good decision. This allowed us to keep everything we had in the project, and just we nibbled away the C code release after release, so we could still add new features, ship new version regularly, fix bugs. We didn't have to start from scratch and introduce a whole lot of new bugs, and we just progressively ate away the C code and replaced it with Rust. The reason we were able to do that is that it's really easy from your C code to call into Rust code, and from your Rust code to call into C code. So one of the first things we did is change our C code to, instead of generating a binary, generate a static library with a main app function. And then we wrote a very simple Rust wrapper that would call the main app function, and that was our first version. We had Rust. All the code was still written in C, but we had Rust. And then progressively, we replaced stuff. And we did it from both sides, so we attacked both from the outside, where we had our main function in Rust calling into C code, and then deep in the program, we wanted to also make sure it would work for us, for more complicated parts inside. And so we had the C code actually call into Rust code, and then progressively we replaced our main loop, which does all the regular processing on the system, and wrote that in Rust. And so we're still loading the configuration in C, and then passing the configuration as an object to the Rust code, and then having the Rust code do that. How do you do that in practice? When you start doing it, you can really quickly tell that Rust was kind of really well designed for collaboration with C. It's very easy to do it. So in your C code, you say, I have a do something function, which is going to be implemented in my Rust code. It's extern. In your Rust code, you can say, hey, I have an extern C function over there. And then you can just call back and forth from both. It gets more complicated, obviously, when you need to pass data structure. I'm not going to get into that topic today, but if you're interested, we can talk about that. But there are lots of tools that help you do that. What I will get into, though, is how do you build the project once you have C code mixed with Rust code. And so the way you do that is you add a build.rs file as part of your project. The build.rs basically prints information on the console, that does things, obviously, and then can print information which are passed to the compiler. So you can generate a library and then print a special command on the output that will be parsed by Cargo and will add linker flags that will be used later on in the linking process of your Rust code. And so in this example, if you just have a C file that you want to link, you just have to the first line will say, if my C file changes, please rerun the compilation process. And then the second one uses the CC crate, which will automatically invoke the GCC compiler, passing all the cross-compilation arguments. So this works well even in the context of cross-compiling code for your target. We'll compile this into an object file, and we'll link it into your project later. And then in our case, we were using CMake to build our project, which was now a static library. And so there's a CMake crate, works very similarly. You call the CMake crate from your build.rs. You pass all the arguments you want to CMake from your build.rs. You can take Rust feature flags and convert them into CMake arguments. And then the output of your CMake project will be linked inside your Rust binary. So that's how we approach this, and this worked great for us. I would totally recommend this approach. So now we need to learn some Rust. And it's funny that we landed on similar books, me and Fabien. These are amazing. Programming Rust, Fast Safe System Development, great book to learn Rust, learn about the API, get like a first book in Rust. Rust Atomics and Locks, really enjoyed that. Goes into the nitty-gritty of how mutex are implemented, how channels are implemented, shows you how to implement them from scratch, then goes to show you the difference between how mutex will translate into assembly code in Intel and ARM processor, really, really interesting stuff. Strongly recommend that book. It's available for free online as well. And then Rust for Rustaceans from Jan Giekset. If you don't know Jan, is a great source of teaching material for Rust, and I can't recommend enough what he does, included in his 6 hours video on YouTube where he walks you through optimizing a Wordle solver. It's just he has some really cool stuff. Anyway, You also have the Rust programming language book, free resource online, great stuff. I would put that really in the beginner category probably. It will get you started, but you definitely need more resources. Reading the doc, someone told me when I started, go on the doc website and read the page for vec, string, bathpuff, option, result. You'll learn a lot of interesting stuff. Took me months to do it, and I should have done it earlier, so I'll repeat this advice. There's a lot of great little APIs that you don't really know about initially that are detailed there. I would strongly recommend that. And then, to really learn, what I did personally is go through Advent of Code in Rust, great way to become more proficient with the language. Watch a bunch of YouTube video, Young was great. And then if you're doing this in a professional capacity, which obviously we were, I would recommend getting some help. So in our case, we work with James Mons, and he doesn't know I'm giving him a shout out here today. But he works with the Rust Embedded Working Group. He's a freelancer, so he's available to do a few hours here and there. We asked him to come a few hours a week and just answer our questions. So he would participate in some code review on GitHub, and then we would grab him, and so we would have a notepad with a bunch of questions. And when he came, we're bombarding him to why is the language so broken? How do you do this? And he would tell us between our feeling, what. We had different good solution, and it would help us be well, this is more idiomatic, or most people would choose that, And when you're just starting, it's really helpful to have that kind of support. Lessons learned. So, these are the few things we learned along the way as we were starting to write Rust. And so the first one is the borrow checker. Everyone is in a Rust talk is going to talk about the borrow checker. You guys are going to have a love and hate relationship with the borrow checker. But I'm here to say you need to fix your relationship with the borrow checker. You need to love and embrace the borrow checker. And it's going to tell you things like this, those really well-formatted, colorized, output, where it's talking about moving, and it's talking about ownership, and it's giving you suggestion on what you can do. And my advice to you, and as I was working on this slide, I realized I think we've been trained, to react very instinctively to compiler error messages. Where we see an error message and we try as quickly as possible to get away from the error. We've almost this reaction where we're we know, oh, I see this, I know what to do, But my advice to you is to take a break and read the error message and really try to understand what it's telling you, because that's how you're going to learn what move and ownership really mean in Rust. And the moment you start to understand what it's telling you, you'll be a much better Rust developer. You will have definitely graduated to the next level on your journey. And so really taking your time to read the error message, I think, is really important. And then, sometimes you can just follow the advice. Sometimes the advice is not that good. But I think what I'd like you to avoid is exactly what the compiler is suggesting here, is to just put clones everywhere in your code, or, just frantically adding and removing references. Try to understand what's going on first. On this topic, another big lesson we learned is that as we were starting with Rust, this is the kind of code we would start to write. And so if you know a little bit of Rust, you can see that we've introduced lifetimes here. We have the apostrophe A on the client here. And so what we're saying here is that we have a struct that has a lifetime that is equal to apostrophe A. And so we initialized it with a reference to something else. And so as long as this memfold dconfig object here is going to be a valid reference in memory, then this will be valid. But as soon as this one gets dropped, then this whole thing won't be a valid reference anymore. I'm not trying to teach you ownership here, but my point is we were making our lives really complicated. And so at the time, we were really proud because we're look, I can use lifetimes. I must be a really great Rust developer, and I'm not copying any byte of memory that I don't need to copy because I'm just reusing the references, and with the lifetime, it all works. But you end up with very complicated code really quickly. When you start having multiple objects, multiple lifetime, this gets really hard to understand. And so I would say the pro Rust version, and this was something that also James helped us with, is to get rid of the lifetime and say, hey, we only do this once when we're initializing the program. It's okay to copy a string. In our C code, we did call stringed up a few times. And And so we're just doing the same thing here. We're just going to copy the memory and get rid of the lifetime. It's going to make our life a lot easier. So I think what I'm trying to say here is that excessive use of lifetime should be considered as early optimization. We all know that's bad. You know, don't over-optimize early. Keep things simple when you're starting, and then you can make your code more complicated once you've figured out the critical path. The other thing I wanted to touch upon are errors and exceptions and crashes in general. So I think there's this general feeling that, you know, Rust will protect you from crashes, you know. And as I talk to more people that have adopted Rust, you know, people are like, oh yeah, Rust is great, you know, protects you from all those errors and stuff. And yes, it's true, but if we want to be slightly pedantic, and it's going to be important here, Rust will protect you from unexpected behavior, you know. It does not protect you from crashes. So it will protect you from unexpected behavior as long as you stay away from unsafe. But there's a whole category of errors that you are still going to run into. So one of them is you call unwrap on a result, you know. And so if you're not familiar with Rust, you know, calling unwrap will just extract the return value. And if the function that you call happened to have returned an error, the program will just panic at this point, which is Rust's way of saying it crashed. And so you'll, at runtime, you will get like this kind of dirty error. Another, like the unwrap is kind of easy to see in a code review. Another more subtle type of error is you initialize a vector of length 1, and then you try to access element at index 42. And that is also a panic because that's accessing an element that does not exist. And so I think it's really important to remember that Rust is not going to protect you against these kind of errors. And so what we do is that in code review, we treat unwrap, expect, etc., as we would treat asserts in C. So we only put them in places where we think, well, if we got there, you know, it's probably better to just crash the program, let systemd or something else restart us, and not, you know, try to deal with the situation that we're in because we don't really know what we're doing now at this point. So that's one thing. The second thing is it's important to understand that when you have a panic, your entire program does not crash, but just the thread that you're in. And so if you have a multi-threaded program and you panic in one thread thinking, oh, I'm just going to tear the old program down and restart, well, actually, maybe you've just killed one thread that was doing the processing, but the main thread that's sticking in the network request, you know, it's still happily collecting incoming data and pushing it to your other program. So think about what's your model for when a thread panics in your program. You know, how do you make sure you take down the entire program down, or you take the entire program down? So having a strategy for dealing with crash thread. And talking about threads, I wanted to talk a little bit about concurrency, because I think for embedded developer, you know, even experienced one, you know, concurrency is always like a hot topic, you know, something we approach very, very carefully. And, you know, you're going to love Rust when it comes to concurrency. Like, once you get comfortable with the borrow checker and ownership, and you start understanding and being comfortable with those concepts, the whole, how it applies to a multi-threaded program is quite amazing. And being able to really share memory between your thread, knowing that you can't really get into undefined behavior because the borrow checker is protecting you is really a big plus of Rust, in my opinion. One thing I stole from Jan in his book is he says there are 3 models for concurrency in Rust. One is you do shared memory with argmutex of a struct or some kind of object. The other one is you have a worker pool where you have a bunch of workers that are all pulling from the same work queue. And the last one is actors, where you have independent threads and they're all basically listening on some queue, probably a channel, with incoming messages, and then processing them. We initially, you know, we're also learning Rust. You know, we want to try everything the language has to offer. And so we did a little bit of everything in our program. It pretty quickly got a little bit messy, you know, where we didn't have like one standardized way to do things. And so my advice when it comes to concurrency is to pick one paradigm and try to stick to it in your program. You know, they're all pretty comparable, but choose the one that's best for your program and try to stick to it. Like, have a conscious design decision and discussion in your team about that. I think that's important. And then another big thing that I took also from some of those books is that the board checker will protect you from undefined behavior. It's not going to protect you from deadlocks. So it's still something that you have to keep in mind as you're writing your multi-threaded program and you're sending messages back and forth. It's like you don't want to be in a situation where you have multiple threads that are waiting for a response from a thread that's busy waiting for something else. So that's what I've learned about writing the code itself. And then once we start shipping code, we start thinking about optimization. And so the first optimization I want to talk about is what happens when you compile your first Rust binary, your hello world, and you look at how big it is. And you're like 4 megabytes for hello world. What the hell is going on? Everyone told me Rust was going to work on embedded. They lied to me. And then so don't panic. There's plenty of stuff in your binary by default that you probably don't want when you're shipping your code. So the first thing you can do in your cargo toml is strip your binary when you're building it. If you're using Yocto, Yocto will do it for you automatically, but if you're just SCPing the file to the target, you might want to do that. So that will obviously make your program already a lot smaller. You want to optimize for size. So you can choose different optimization. S and Z are the two available for size, so play with them, see which one gives you the best results. And then you want to remove the default panic handler because the panic handler is actually pretty big, so that's the thing that takes the crash and gives you the full stack trace if you want it on the console. So if you remove all of that, you get to 372 kilobytes. Who's satisfied? Someone is satisfied. Okay, we got a few people that are on the fence. They're like, yeah, it's much better than 4.4 megabyte, right? But it's still pretty big. So let's have a look at what's going on. And so I want to introduce another program that's going to be your friend. It's called cargo bloat. And so you install it with cargo install cargo bloat. You do cargo bloat -- release -- crates, and then prints a list of all the crates in your project, and it tells you how big each crate is. So, we was hearing some comments about NPM before the talk started. If you're if you want to kind of keep an eye on how big all of those packages that you're adding to your program are, this is really useful. And so what we can see here is that our Hello World section itself is only 56 bytes, but we have 258 kilobytes of the standard Rust library. And so it's important to know that when you're building a Rust binary, the Rust standard library is statically linked inside your binary in every single binary that you will produce. And the Rust standard library includes a lot of stuff like access to input-output, access to the file system, a lot of really useful stuff if you're writing program for Linux. But it's pretty big. And because it's pre-compiled and not compiled every time, the compiler can do some optimization, but it's typically not great at really shaving off everything you're not using. So one thing we can try is get rid of the standard library. And this is actually pretty accessible and easy. So if you're working in a really constrained environment where you're really looking at every kilobyte, this is totally realistic. You write a program, you say, I don't want std, I don't want main, I don't have a main function, I'm going to provide my own main function. And then you just export a symbol called main, which returns an int. And then in this example, I've used another crate called libc println, which allows you to use the standard C library directly to print stuff on the console. And so you also need to provide a panic handler in that case because that's also part of std. And by doing that, I get to a binary that's only 1,275 bytes of code in the code section. The entire binary is 14K, I think, 16K in that case. And so that's already like, at this point, it's much, much better. And so now you might say, how much space would the same program in C take? And so I compiled a very simple hello world in C and compared the size, and now my Rust binary is smaller than your C binary. Who's impressed? So my takeaway is not that you should necessarily do that, but I think what you need to remember from this is that the Rust STD library is about 260 kilobytes. It's linked inside each binary. If you're really sensitive to space, you can just work without the standard library. So, you know, options for you now that you know this information. One is you can work without the standard library, but that will prevent you from using a lot of crates on that are part of the cargo ecosystem because they depend on STD. There are a lot of crates that are really useful, like SERD, for example, for deserialization, that have a mode, you know, they have a feature flag to work without STD, so it doesn't prevent you from using everything, but it will definitely limit you. And that means you're probably going to be using a lot of direct call into the C standard library if you need to do like file system access or stuff like that. But if you're just writing a very contained program that has very little input, output, little interaction with the system, and it needs to be really small, that might be a good strategy. Another technique you can use is you can keep chiseling away and trying to reduce the size even more with STD. And so the next step to go lower in size than 260 kilobytes is to compile the standard library from source, because if you compile it from source with your program, the compiler will be able to do a much better job of eliminating dead code. And so if you're interested in that approach, the min-sized Rust repo is a great resource, which really goes down that rabbit hole pretty far to get a super tiny binary. And then, you know, the last option is you can just embrace STD. And if you're writing Rust for Linux and you're not like at a few hundred kilobytes plus minus, you know, I think that's a great approach. So at this point, the concern is that if you have multiple binaries, you're going to copy the standard Rust library multiple times on the system. We thought that was not really acceptable for our use case. And so what we do is that we use a BusyBox approach where we ship one binary that's actually linked multiple times on the disk as hard links. And so depending on the name that you use to call the program, it will behave differently. And so that way we've like factored the standard Rust library, and we only have it once on the disk. If you use that approach, you're going to have access to the cargo ecosystem. You're going to be using library. You're probably doing something that's going to be a little bit bigger. And so the second round of optimization that I want to suggest you look at is libraries. And so what we saw is that in Rust, you have love Rust because it is opinionated on a lot of things and it's guiding you, but in some places you still have options. One place where you have option is SSL. You can decide if you're going to use a full Rust implementation of SSL and the whole TLS transport layer, or you can just link into libSSL, which is already part of the system. So this is what it looks like. You know, you have your Rust binary. You can decide to use the Rust TLS crate, which is a full Rust code that's going to be built in, and that's going to make your binary bigger. Or you can use the OpenSSL crate, which is just a thin layer of Rust code that wraps and then call into the .so libSSL on your system. And that is definitely going to be smaller. So the good news, it's very easy to experiment with that in Rust. You can use the feature system, and for example, with the request library, you can decide which SSL implementation you want to use very easily with feature flags. And so if you compare the size, now you get 2.4 megabyte if you're building in a full Rust SSL implementation, or 1.5 megabyte if you're using libSSL on disk. And yes, you also need the 700 kilobyte of libSSL on disk, but you probably already have them on your system, so at this point it's not a big concern. And so we've seen that this approach actually works for a bunch of other libraries as well. So libz, they're depending on what your project is doing. I recommend you look at different options because you will typically have the choice between using a full re-implementation in Rust or linking into something that's already into the system. You know, like images, videos. You know, you're going to have the same kind of options. So we've been doing this for 18 months. What's our conclusion? You know, we love Rust. Our code reviews are so much more interesting than they were before. You know, I can't say enough how much of a benefit that's been. We've really enjoyed, instead of like looking for memory leak, we can actually discuss the architecture of the code, and that's a benefit we did not anticipate. And then another benefit we had not seen coming is that we will never read and write C code the same way. You know, Rust, understanding ownership and this whole like logic of the borrow checker will change the way you think about memory and you read C code in the future. And that's it. Thank you very much for coming today. We have a booth upstairs, Memfold, so if you want to continue the conversation, I'd love to see you stop by, and if we have maybe a few minutes for questions. So, yeah, thanks. Any questions? Yeah? Hello? I don't know. Yeah.
So I'm not super familiar with Rust, but I was just curious, you discussed the BusyBox solution. Rust doesn't support dynamic linking. You couldn't just put the common crates in a library that's shared between your tools?
You can dynamic link to C libraries, but not to Rust libraries.
Why don't they support that?
Well, that's a great question. It's why I don't think I can answer that. It's not supported today. You can only produce a static library with cargo.
But if somebody were to implement that, maybe it would be very useful.
Yeah, it's not that easy. I did look into that when we were getting started. I think if it was easy, it would have been done already. You know, like there's no good solution today to distribute dynamic libraries in Rust. Yeah, I hope that's something the language improves on in the future. But I don't think there's any effort that's gonna come to a result.
So it's something about
term.
the design of the language or something that's hard to, like.
Yeah, I don't want to
decouple?
say. Do you have does someone have a better answer to that question? Yeah. Okay.
Sure.
That was also one of my questions. I was wondering if you were compiling or targeting some special platform that doesn't support that. So Rust strictly does support dynamic libraries. There's a C-style dynamic library, cdylib. There's also the rdylib, sometimes just called dylib. So, but it's really platform dependent. So I noticed, I also had a similar question about the BusyBox approach. The standard library specifically, you definitely can depend on that dynamically. It just depends on the platform. I don't know if you have special constraints or something.
No, so we don't have special constraint, but you know we're limited by the tools that are available. You know, maybe I should have been more specific. Like if you look at the cargo ecosystem, you know, we're not distributing a dynamic library, and if we're talking about optimizing space on one machine, yeah, in that case we control the whole compilation environment. We could probably take some of our code and put it as a dynamic library, but the BusyBox approach was just the option we chose in that case. But do you see a way to link to cargo packages dynamically? I don't think anyone does that.
Yeah, this is actually an issue that I've spoke with the cargo and Rust teams on at great length over the years. Yeah, you're right. It is hard to distribute a precompiled. I assume you're talking about a precompiled dynamic library artifact. Right.
And do you know why?
Yeah. So a lot of it has to do with the lack of a stable ABI. Okay. That's one of the main issues, and some folks are working on it, like Eminu is working on that. Josh Triplett has also worked on that over the years, but it's not yet there.
Okay.
But yeah, so you can hack it. You can hack around that. You can precompile something. One of the issues is that like rlib and rmeta, the metadata that the compiler outputs about a particular artifact is not stabilized, that format. So even if so ideally you could have something like, you know, a library that only works when compiled against and reused against the same exact version of the compiler, which you can do. That's not officially supported, but it's possible through some hacky invocations of Rust C, but this is not something that the general public should be consuming, so I don't want to pretend like it's easy.
Yeah.
Anyway, I won't take up any more time, but yeah.
No, that's great. Thanks for contributing. Yes, there's a question back there.
So you switched over from C to Rust.
Yeah.
Was it the preventing unexpected behavior, borrow checker, and memory management that led to that drive? That would seem to me like quite a big initiative.
Great question, thank you. I don't want to talk too much about the reason why, because I feel like everyone is always giving the same reason why. We were mostly, we had a roadmap ahead of us with a lot of features that involved, a lot of like manipulating JSON, uploading files, doing a network connection back and forth. And it was just really tedious to implement in C. Like we started by taking our microcontroller SDK, porting it to Linux, and so that was all C, and then we just kept the C. But then as we started, adding more features that made sense on Linux, it just was getting really tedious to do that in C, and we were looking for a more modern language that would be a little easier to work with. So I would say that was the number one factor, is like we thought we would be more productive in a different language, and we haven't been disappointed at all. I think the productivity is definitely there.
What were the other languages considered?
We did look at Go, we considered C++, we considered Python. Didn't choose Python for distribution and memory requirement reason. So we did look at some other option. And when we chose Rust, we didn't have a lot of experience. We had some people that had written some Rust, but not a lot inside the company. So it was definitely a little bit of a bet, and that's why we did it progressively over time. Any other questions? Yeah, in the back.
I was curious. Was the migration process from C to Rust, was that mostly manually done, or did you use tools like C to Rust?
That was almost completely manually done. We also used this opportunity to introduce, a lot of like Rust structure, like objects and everything, which did not really exist as such in the C version. So I don't think we could have really automated this completely. Like we could have taken the C code and just translated it into Rust, but that's not what we wanted to do. We wanted to introduce more objects, traits, have something that would look like idiomatic Rust.
Thank you.
I was curious if you used any async in the project, and if you did, what you went with, what went well, and what could be done better.
Thank you for asking the question. When I was working on the slide, I thought, do I throw in async or not? And it's definitely another kind of paradigm for concurrency, or you could argue that you can do the three other within async. We decided to not use async initially, partially because we didn't have a lot of experience with async. We didn't have a lot of experience with Rust to begin with, but we didn't have a lot of experience with async. And we thought, we don't really see a need for it immediately, so let's start with that. We also didn't want to bring the whole like Tokyo executor and all of this, because we thought, that's just going to add more code size that we probably can live without. So let's start without async. Then along the way, we hired another engineer. So one other benefit of Rust is that it makes it much easier to hire really great engineers. So we hired this great guy who comes from Amazon and had a lot more experience writing async code in Rust. And so we've had a lot of discussion over the month over when do we switch to async or not. Because along the way, what we also realized is that some of the HTTP libraries and networking libraries we're using, they're using async under the hood anyway. So even if you're using the blocking API, they're still like spawning an executor and then doing the thing asyncly inside the executor. So anyway, we have not done the jump to async yet. One of the big reasons is that if you start using async, you basically need to change everything in your program to also be async, because if you start calling a blocking function from async context, you're going to block the thread it's running on until you return. And so there's just, we haven't felt the benefit, outweigh the cost at this point. I don't think we will switch to async on this project at this point, to be honest. But it's definitely something else to consider as you're starting your journey in Rust. And maybe the data point here is that not everything has to be async. Rust without async is still a very valid option. Anyone else? Yeah.
What did your transition look like for unit tests? What framework did you use?
Yeah. Yeah, I removed those slides because I was already out of time. But we were using I don't even remember. I think we were using a CPP unit in C, and we use rtest now. We like rtest because it gives us something we have in our Python code base, which is the ability to have a fixture and to have test cases. And so the built-in test framework is already really good. rtest gives us those little, mostly syntactic sugar, that we thought was kind of nice to have. So that's what we use. Yeah, and then another thing we do for testing is that we run our code inside QEMU, and then we have Python code to poke at QEMU and do full integration tests, but that was not really specific to Rust, so didn't cover that today. Yeah.
Follow-up question that, in a similar manner, since Rust kind of helps protect against undefined behavior, what did you guys use for static analysis, even going from C to Rust? So like CPP check or covariate scanning, and what did you do for the Rust side?
We don't have anything specific besides what you get from the Rust compiler and Rust analyzer. And that already gives you a lot of check in Rust that you don't get in C. Yeah. So yeah, I'm not going to have a lot of experience to share on that.
Yeah, for static analysis, would call out Clippy, and that's
yeah, we use Clippy,
in
of course.
Cargo.
Yeah, Clippy is amazing. Yeah, especially as you're learning, because Clippy will also teach you a lot of idioms and teach you a lot of like, hey, you should probably do this because this is the Rust way to do it. Yeah. Okay, one more question, and then if anyone wants to kick us out, let us know. I don't know when the next talk starts.
Hello, thank you for the talk. As someone relatively new to Rust, how do you view the market trends in Rust adoption? Is it coming to a point where knowing C by itself is no longer sufficient? Like, where do you see kind of like the projection of Rust adoption?
So Linus Torvalds this morning was saying that he tries to stay away from the hype. So after that, I was wondering, does he see Rust as a hype or not? I don't know. So to answer your question, I definitely don't think Rust is a requirement. I think Rust is honestly a great language for embedded. We have a lot of people on the team that have been doing embedded for a long time, and we think it really it's nice to have the nice things that other people have in other language and have them in a language that we can use in embedded. Maybe that's one way to put it. And so I'm happy to see more Rust adoption in general. We use Rust on user space Linux, but obviously it's growing in the kernel. It's also growing on embedded platform. We see more and more customers on microcontrollers using Rust directly on bare metal platform. What Espressif is doing around Rust is really interesting. The Rust embedded working group is really active and trying to keep all the platforms working in one embedded HAL layer. There's I think there's a lot of smart people working on this together, and we're just excited to be a part of this. If you're starting in the business and you're not sure what to do, I think it's going to be hard to be an embedded engineer without a C background still today. But, yeah.
Thank you.
Okay, well, thank you very much, everyone, for coming. If you want to continue the conversation, we'll be around on the Memfold booth in the Solutions Hall, and happy resting. Thanks. Thank you.
Good work.
Works? Yes.
live.
One of my colleagues here, maybe he can come on with
Okay, there's a switch.
And something I was asking one of your colleagues when he did. Almost.
Okay, I think I have sound. I suppose if somebody comes, they can catch up because it's time to start and beginning anyway. First, I'm going to introduce myself. Welcome everybody to this talk. I'm going to be talking about WP WebKit and what it can do for you, or from the point of view of how it can be integrated in many ways in embedded devices or in any kind of product. And I will try to, my goal here is to get you some takeaways, like what can it do for you, how to integrate it, and what are some best practices. I've been working for Igalia since a lot of time ago. It feels like a full life, 2008. And I've been doing WebKit since 2012. And lately, well, the last 8 years maybe, I've been doing improvements on the platform layer, which is the part that integrates with the rest of the system. Hardware bring-ups and release management. So if some release is broken, you can blame me if it doesn't build from a release. And lately I have been getting into old computers as well, and I'm not going to talk about those because those cannot run web engines, or modern ones at least. But it's pretty fun. It's pretty fun. I like the Amiga I got recently in particular. Anyway, like I was saying, I'm part of Igalia, which is an open source consultancy that has existed for a long time. It's headquartered in Spain, and we have fully remote structure. And if you take out the original creators of web engines, let's say you take Google out of Chromium or Apple out of WebKit, we're the main contributors to them all, basically. And we have contributions in many other open source projects. And we're also members of many open standards group. We think it's important to be there as well. And if you want to talk to me or to any of us after the talk, there's going to be, I'll try to leave some time for questions, of course. But we have a booth upstairs as well, and you're welcome to come and talk with any of us about any of these topics or any other topic you may find interesting to bring up. And like I was saying, my plan is to give you a very quick rundown of WP WebKit. Some notes about what would be a typical process of getting it into your device, and once we get it there, how to maintain it, how to be up to date and incorporate newer versions, and I will give anyway at the end a small summary of the main key points of all this. And my goal is that you go back with the idea that yes, if I need a web engine, WP WebKit can be a good option because it's quite adaptable, and I think that's one of the main strengths. Like, it's designed to be portable in the sense that it can be adapted to specific platforms. That's something in general about WebKit. WebKit, the project, is not only Apple doing a web engine for Safari. It has customization points. So, for example, on Linux, we can use a different painting engine, like we can use Cairo, or lately we have been moving towards Skia, or we can use a different networking stack. So we can have a complete build of WebKit that doesn't depend on any proprietary component from Apple or from any of the other ports. Like, for example, there's a PlayStation port that also uses some specific components which are not open source. And in particular, WP focuses on embedded devices. And it's full open source, like I said, and this is the part, a web engine is the part of the browser that does the painting and handles the web content, processes user input, and gives you something rendered that you can show to the user. But it's not a whole browser, and that's an important distinction here. So you can think about it as packaging the part of web browser that handles the web content into a separate library that then applications can use. And it has a multi-process architecture these days, well, it has been for quite a long while. I will just touch very quickly on it because that affects some bits about how it can be customized, but it's going to be very brief anyway. So you may be wondering, why should I put a web engine in my product, in my device? Paraphrasing someone else, the web is in the world. It's everywhere. Like, you have even native or so-called applications, which are basically web content inserted into the application, either taking the full space of the application or some part of it. There's, well, there used to be this moniker that there's an app for that. I would like to reach to the point where we can say there's a website for that, so we don't depend on particular applications, and anyone with a compliant user agent, with a compliant web browser, can access the same applications without needing, without mattering that they have an iPhone or an Android device or whatsoever. That would be great. And we're also at the point, or we have been at the point for a few years now, that embedded devices are powerful enough to run a full-fledged web engine. There may be the case still sometimes that we want to trim it a bit and cut some parts that maybe our device is not going to use, which is also possible. But in general, we can just pick any contemporary system on chip released in the last 10 years, and we can throw a web engine at it. It will perform better if it's newer, of course, but it has been possible for a while. And also another thing that is nice of web technologies is that anybody can put up some HTML, prototype something quickly, and then iterate over it, and that can be quite fast. You don't need to be rebuilding full system images to test your changes to your application or to your part of your user experience that is done using web technologies. And that's a strength that we don't see with every kind of framework that is there to do user interfaces. And I think that's one of the selling points of using web technologies. Like I said, WP is particularly designed to be embeddable. It's platformless from the point of view that it doesn't depend on a toolkit. So you don't bring with it the dependency on GTK or Qt or any other kind of graphics toolkit. So you can tack it on anything as long as it can render the web content, it has some GL support, you can get out something that is painted frames of web content and give it user input. So that's the point of being platformless, that it allows to adapt it to many situations and many kinds of devices. And like I said, it can be extended. We will touch on this because I think it's important for embedded devices and custom user experiences. Quite adaptable as well. Like I said, just a moment, one example is that you can trim it down and disable some components you may not need. Like, for example, you can disable the multimedia support and have a build that only shows documents and doesn't show videos or audio, for example, which can be interesting for some devices. And the set of dependencies it has, therefore, is quite minimal, which can be a strength as well. And also, it has been available for quite a while. Nowadays, it's upstream, ready to pick from build systems typically used on embedded development. You can find it in Yocto. People from Igalia, some of my colleagues actually maintain the Meta WebKit layer, where you can get the recent versions first, basically. And usually we try to keep work in the last and previous to last, and sometimes the previous one still, versions of Yocto. So any version of Yocto typically that is from the last year and a half or two should have the possibility of have the latest version. It's available in Buildroot. I maintain the packaging for Buildroot myself. I have pending an update to the latest release, but basically it's going to be done in the next weeks after this, after the conference. And PTX-Dist also has packages, but nobody from Igalia maintains them. But last time I checked, they're quite up to date as well. It's also available in distributions, so you can use apt on Debian or Ubuntu, install a release that is relatively recent, on Arch Linux as well, and you can get a taste of it in your desktop. It works on desktop as well. And I was checking the other day the first commit for WP, and it's 6 years old already. So that's a pretty good track. Not as old as WebKit, of course, but pretty old by now in terms of technologies that are used around IT. And it's actually a little bit older. It started life, this is kind of an anecdote, as WebKit for Wayland, and then it was renamed. So it's actually a little bit older than 6 years. Very quick introduction about multiprocessing WebKit. As a modern browser, it tries hard to be able to isolate sites from each other and protect the user from, let's say, malign websites trying to sniff on others and so on. So the main thing is that there may be multiple web processes. So you have your browser or your application that embeds the WebKit WebView widget. That's like the main entry point in the API. And then that automatically spawns as many web processes as it needs to handle web content in different sites. Usually it's one different process per site to achieve this isolation. And one network process that takes care of fetching resources from the internet and so on. And this separation also allows to sandbox the different processes and, for example, not give any networking capabilities to the web process and so on. So this is security features that come built in with WebKit. And this will come in useful to explain a thing that I have later. So first thing is, if I'm considering to add a web engine to my device, my product, whatever I'm doing, first, of course, the first thing I'm going to do is check whether my hardware is supported. We do have hardware support list in the web page. It is fairly complete from the point of view that it has all the devices that we have personally verified that it works reasonably well, or that we have first-hand reports from people we know that have tested it. That doesn't mean your hardware is not supported. That means it might be or it may not be, as you can imagine. So if it's supported, perfect. If it's not, well, this is something that people usually don't think much about it, but there's a number of requirements that if your platform, if your hardware meets them, it's very likely it's going to work, either with existing integrations or with some additional work bringing up the hardware. The bare minimum we have is we need GLES to support. I will get into this later as well. We would like to increase the requirement to 3.0, but there's platforms we want to support that are still in 2.0. And some mechanism for sharing graphics buffers between the different processes. And this is one of the places where the multi-process architecture intro comes handy. We have the web content process that renders it. Once it's done, we have to pass this to the user application, which is in a different process, so it can be displayed. So, of course, we need some mechanism for moving buffers in between those processes with pixel data. Ideally, we would recommend you try, if you are in the position of being able to choose your NAS hardware, please pick a 64-bit system on chip or CPU. That helps a lot. And there is a number of EGL and EGLES extensions which they're not strictly required, but make things more performant and definitely help, especially with the part about passing buffers among processes. I would say the most important thing to keep in mind for new developments is try to get something that supports DMEA-BUF, which is the kernel, Linux kernel buffer sharing mechanism that I think it's kernel 4.3 onwards or something like that. So it's nothing new, and it should be the best option because it avoids copying pixel data. Like, it doesn't do it in every case, but there's the possibility in many cases of have the buffers that are painted, directly pass them through different processes, and they can get to the display without doing any further composition, which is the best possible outcome from a performance point of view. And tying in with GL support and buffer sharing and so on, I would like to talk a bit about issues we have found that makes things more complicated when bringing up WP on hardware, embedded devices especially. And we have, I think the main issue until recently is precisely that the DMEA-BUF support or the Wayland support even has been missing sometimes or deficient at best or has been buggy. And I could give examples, but I don't want to blame any any vendor of drivers. Like they do hard work, and making drivers is not easy. Nevertheless, the situation is getting much better nowadays, and basically, most of the new system on chips I have been seeing lately, most of them either have Wayland support, which is good and stable, and or DMA buff support, which is the best possible option. There are still many proprietary drivers that support only GLES2, which is the reason why we keep it as a baseline. And then this is a funny thing. A very modern system on chips may only have a Vulkan driver, which is not necessarily a problem, but we don't have direct Vulkan support in WebKit. So what we can do, for example, is use Sync, which is a component that comes in Mesa, which is a GL driver that is under the hood implemented in terms of Vulkan. That works with WP today. I have tested sometimes on Intel GPUs and also on Radeon AMD GPUs. And it generally tends to work, but it's not as well tested as a driver that directly supports GL. And I think the worst case that I have found is cases where there isn't a driver, or the driver is basically impossible to use. And in some cases, we have used Mesa's software rasterizer in some devices. That's not an option I would recommend at all. It's going to be doing all the rendering in the CPU. If your display is small, maybe an option. We're talking hundreds of pixels by hundreds of pixels. A modern CPU can keep up with 60 frames per second on a reasonably small screen. So if you have a very small device with a very small screen and you don't have the possibility of adding a GPU to it, it may be an option, but I would say shouldn't be your best option, your first option. And something that is a recurrent topic is open source drivers tend to work more reliably. And even if they don't, something we can do is dive into them, find out where the problems are, and sometimes even suggest the improvements needed ourselves. And this ties in a bit with having colleagues at Igalia that have knowledge on this, because we have a graphics development team as well. So we can directly ask people who know, like, I need this from Mesa, from this driver. Can we make it work? And from that point of view, it's much better to have open source drivers. Then another kind of situations where it has been a bit tricky to get WP working is when the hardware is somewhat a bit odd or has some limitations. Like, for example, if you have a display panel which is only 16 bits per pixel. We have, a couple of years ago, added a kind of escape hatch that you can hard code which kind of pixel format WebKit is going to use to use 16 bits per pixel, but it's only that case covered. So we may need to patch WebKit if we need a similar escape hatch for other pixel formats. That is something that improves with DMA buff, because in that case, we can get from the kernel the information about which pixel formats the hardware prefers. So that works much better. But while it's possible to get, for example, non-32 bits per pixel modes working, it's less tested, of course. So I would recommend to either have drivers with DMA buff support or go for a 24-bit per pixel or 32-bit per pixel display, which makes things more tested and reliable. Then we have the situation of, this is funny hardware in the point of view that you may have your device that is standing on a table, let's say, it could be a speaker, let's say a smart speaker, has a screen. And maybe the screen is physically attached in a way that the bottom part of the screen is in the top. So we have to do the render flipped around or rotated. Flipped is usually fine. There's flags inside WebKit that can flip the whole rendering. That's okay. Rotation is a bit trickier. If you have a display that is designed to be a landscape and you put it in portrait in some device, well, that's the kind of case. It also works. It's quite reliable on Wayland to do that because the compositor takes care of it. We have some support to directly use rotation on DRM, direct rendering kernel mode setting devices. It works. It's a bit less tested and doesn't cover all the possible corner cases that a compositor may be handling for you, but it can be made to work. But it's a thing to keep into account if you want less trouble to get things integrated. Try to avoid, especially the rotation modes. But it should work anyway. And then sometimes we have some situations we have had in which we had to attack the hardware directly. So instead of going through the kernel or going through an existing compositor, we may need sometimes to access a screen to render using some SPI interface, for example, or some legacy frame buffer device interface with a driver that exists but cannot be updated to do DRM and kernel mode setting, for example. This is doable. The trick with it is it's not one of the methods for accessing output screens that is built into WebKit or the existing browsers. So then it's going to be a bit more of development because you're going to need to do this thing of picking each render frame that comes from WebKit and handle yourself how to push it to your screen and so on. The possibilities there is, and sometimes it's what you need, but it's usually a bit more tricky than something that is commonly tested, of course. Then, of course, once you have gone over your hardware, what is supported, what not, you need to add a browser to your device. And we have, in order of increasing complexity, we have COG, which is kind of a reference browser, like a single window, even though it's getting support for multiple ones. Anyway, it's a program. You can run it. It works. It may be that it doesn't do what you want. You may want to embed something into something else, make your own browser, design your own user experience. It comes with a library that you can reuse. So, for example, you don't need to implement a Wayland client that picks the frames from WebKit, pushes them to the compositor, and yet you can, for example, add some user interface around the web view and do your own thing without writing everything from scratch. And of course, you can do your own thing completely, just get raw EGL images from WebKit and paint them into a, I don't know, texture cube and have websites rotating into a cube in one website in each side with different web views. You can do that too. There's one option that I don't have here mentioned, which is we have a new WP platform library coming up in, not sure if it's going to be September in the September release or the next one, but it's coming up. And it's going to replace COG and COG Core and the library for most cases, we hope. And that comes integrated with WebKit, so you don't need to build a separate component either. So it's going to be nice. Just to give an example of the amount of effort, I'm not doing we're not supposed to read it. It's just to show the difference in code. This is if you reuse the COG library, how very minimal browser, there is just a window with a web page, would be done. And it doesn't have any error checking. The text is quite small, doesn't matter, to give you an idea. This is what we are aiming for with the new API that is coming in either in September or in the March release 2025. We're not sure yet. So the idea is that it should be as easy as this to create a basic one-window browser that doesn't do anything special out of the supported platforms, which at the moment is Wayland and DRM mainly. So that's where we're trying to get. And I think this is probably the most interesting part for some of you, which is which options do I have once I have WebKit running, once I have a browser that shows web content. How can I make that web content interact with the rest of the outside world, outside of the web? Let's say I have some sensors, I have some special input method, like maybe I have like a spinning wheel that is a rotary encoder, or I have some custom keypad, etc. How do we get that done? And the input part is easy. It's basically you push the events through libwp, and they go to the web view. So I'm going to focus more on what the web content can do to affect things outside. And of course, the final goal is to have a well-packaged product that is well integrated. And often we see people rolling their own web server that runs locally in the same device, wasting resources in the device, and adding latency and doing round trips through the loopback interface. Let's try not to do that. I mean, it's an option. Sometimes it's the best option, but there is no need. And we have found that often people don't know that it's possible to do better. So going from the easiest to the more complicated, first we have support for URI scheme handlers in WebKit. So there's this web context object that you can use to configure some parts of how WebKit behaves. And one of the API calls we have there is to register a new URI scheme, which basically you give it a name and a callback, which is native code. And whenever a load happens for an URL that instead of HTTP has, for example, this echo colon dash dash and something, it's going to call that callback. So you can turn any fetch or XML HTTP request or any page load into a native call. And that native call can do anything it wants as long as it returns some content to the client in between codes, because it's all in the same process, but to the client code that is trying to fetch that URL. This is a very silly example that just picks the same URL you get and sends it back as plain text. But you could enable some lights, blink some beeps, and buzz some buzzers, and then return something that says your coffee is ready, and that will be fine. And like I said, you can use any native library or any kernel facility to do whatever needed. That's a bit of trickery with it because it's a cross-origin request from maybe you have been loading your content, your HTML from file protocol, and then you're accessing this echo protocol or some other custom scheme protocol. There's possibility also to set it up in such a way that it works despite the cross-origin request protections that the web engine does. I'm not going to get into that, but there's a blog post that is referenced in the slides that has a link to an example with how to do this. And then the next in order of complication and flexibility is using user-script messages. Remember this, we have web process for the content, we have the UI process, which is where you use the API of WebKit, where you have your browser, your application. This is going to involve some serialization from one process to another and back. But it's easy to use from the point of view that you have this other object that is the user content manager that you can attach different things to it to modify how web content is loaded. And one of the things you can do is register one of those message handlers. When you give it a name, then you can connect to a signal in the content manager, and we'll see how that gets invoked from JavaScript, but this basically gives you a JavaScript endpoint that you can send a payload that is a JavaScript object, which can contain strings, numbers, etc., some data. And you get the data in your callback, which is again native code, can do anything you want. So, for example, here you will get your callback, and you get the GSC value, which is GSC is JavaScript core, is the JavaScript engine in WebKit. So basically, you can inspect this value that you got from the JavaScript code in your C or C++ native code, do anything you need from the data you get, and then send a reply. And the way this works in JavaScript is you get a promise. If you are not familiar with it, it's a kind of JavaScript object that when the request has been completed, either calls a callback that you provide, or you can use this newer await syntax that you can, your JavaScript code is going to be suspended until the asynchronous reply comes. And WebKit handles automatically for you the serialization from the web process to the UI process and back. So this is quite easy to use, and usually when we advise people to use this, and when we see people use this kind of user messages, there's usually some wrapper API in JavaScript that makes it easier to use, and you have some functions that create the messages, and and send them to make it easier to use for the people developing the web applications. And like I was saying, it's asynchronous, there's no message passing. If you need something, if you are doing something that needs performance, this may not be the best option. Let's say you need to pass big amounts of data to some external device that is some kernel driver. Then you may want the complicated way, but most flexible, which is the JavaScript Core API. We saw it a little bit earlier, like you get, with the user messages, you get a GSC value. The native API, you can define new functions, you can define new classes, you can define new objects, you can push values on the JavaScript context, you can do anything you need to implement a JavaScript API. Plus, you have access to array buffers, which means you can pass data in between JavaScript and your native code without copying it. So basically, your native code gets a reference to the data buffer underlying the JavaScript structure. This is a very silly example of how would you make a native function that uses a GSC value to do something with it. It could be anything else, of course. And the thing we need to register native functions or add classes, etc., is execution context. Once we have it, there's a series of functions in the API, for example, to create functions and assign the function as a global, and then we can use it from JavaScript, and it works. Now, the tricky part is, where does this JavaScript context come from? Well, there's two. It's not that there's two ways, but the JavaScript library, JavaScript Core, can also be used standalone. So if you want to make tools that use the same APIs that you have been doing for the web applications to use, you can also use it like a kind of mini Node.js, but without Node. So you can reuse the WP WebKit library to run JavaScript programs on the console, for example. So you can create it yourself. The thing is, if you have a web page, it's more complicated because the whole web engine handles creating the JavaScript context for you. To have your code in the web process, WebKit can load plugins, which we call web process extensions. And there's a certain API that WebKit lets you know when a page has been created, which means there's a new page loaded, lets you know when the window object has been cleared. That's the global for the web content. And then when you handle those signals, when the page is created and then when the window object is cleared, that's the best point to add your own APIs on top. So we basically give you the building blocks to get to the point where, here, now's the GSC context with empty global object that only has the web base standard web APIs. Now you can add your stuff. And it's a bit complex, but it has to be like that because of the multi-process architecture and WebKit handling all the page load and base standards web APIs for you. But it works well, and you drop your plugin in a directory and configure it from the UI process side, telling where to load extensions from, and it will happily do it. You can even reuse existing browsers like Cog and set extensions directory and customize new JavaScript APIs without rebuilding the browser, because being loadable plugins, there's no need for full WebKit rebuild or anything. So that's pretty neat. And some links for whoever wants to check later. It's basically things I've been talking about integrating and extending WebKit with some examples and reference documentation. And once we have everything super integrated with our device, what do we do? Are we going to forget about it? No, we need to update. This may be especially important if your device loads web content through the internet. As we know, software is hard, getting everything right is hard. There's security vulnerabilities, etc. Browsers should be updated, or web engines should be updated. We have had, in the last years, quite a good track record on providing security updates. I would like to point that out, because we have seen many cases in which people get certain WebKit version and then it remains without updates for 2 years, 1 year, 3 years. And then it happens like with the Nintendo DS that because it has an old WebKit, somebody manages to load some HTML that breaks it and jailbreaks it, and we don't want that. Or well, it's nice to jailbreak a console, but if we're the product designers with that hat on, we don't want that. So from the point of view of releases, we do 2 major releases per year. Those are the ones that include new features. But despite that, we try really, really hard to keep the same API and ABI, so people don't need to rebuild their programs. That has worked quite well. And even Debian, the distribution, which is quite conservative, adding new packages, has been picking security updates from major releases, which is, I think, quite an achievement. We do have documented policy for updates and requirements for building, which we have been following thoroughly, and that's what has helped with having distributions pick updates. And basically, we tease them with a carrot of, this is our promise to you, we're not going to add new dependencies, or if we add them, you're going to be able to disable them, so you don't need to update other packages. You can update WebKit only with your same base system. And that has been working well with distributions and also with some customer projects we have had where updates have been shipping quite promptly after the new major releases even. So yes, you should ship the updates. We do try hard to not break things. Sometimes it happens. It's unavoidable. So you may want to skip the .0 major release. Often, a couple of weeks after, there's the 0.1, 0.2, which fixes whatever may have regressed. Most of the regressions are usually built-in regressions, because there's so many different ways and options to build WebKit that it's easy to, for example, do something that breaks the build, disabling the multimedia support that I was mentioning earlier. So that's the kind of things we usually fix in point releases, plus reliability and security fixes. So picking minor releases should be a no-brainer, basically. Those, I don't remember when it was the last time a minor release broke anything. Major releases, try it first, and from that point of view, it's good to do some automated testing. There is good WebDriver support, which is a standards API to control web engine and tell it to do things like a user would do, like search for this button, simulate a tap on it, scroll a bit now, this kind of stuff. So you can test your web applications inside your devices. It's even possible to connect a WebDriver client from, let's say, a computer that has a network connection to your embedded device, run the web engine in the embedded device, and then they talk over the network, and the computer is orchestrating this testing. I think the most impressive setup I have seen, I don't have a picture, was closet, maybe almost as big as this projection screen, with shelves full of devices, all connected with over the network with a computer that was next to it, and they would basically run their base images with the newer WebKits or the newer versions of everything, and do testing with WebDriver automatically to check that their web parts will also work correctly. That's something I want to encourage people to do. Because if there's any regression in WebKit, you are going to likely catch it if you test it. Another technique I have seen is having different integration queues, one for, let's say, regular point releases, and another one for the next in-development releases. So before we do each major release, we usually do some checkpoints where we have development releases, and those usually, they may break things, of course, but they usually build, and they're minimally tested from the point of view that they should build and run reasonably. So I've seen people have a different integration queue that uses the latest development release instead of the latest stable point release. That way, you start preparing for the next major release ahead from its date of release. And then it's easier to integrate a new major version. So wrapping up, and we'll have some time for questions, hopefully. WP is very adaptable. It sure can fit your needs if you need a web engine or if you are considering a web engine. We have a checklist for, well, I showed a checklist for features hardware must support to work, but we have also a list of supported hardware. It's great to check it. If we get reports of hardware that works, we may update it. So if you manage to get WebKit in something, send us a pull request. We'll be happy to double check it and apply it. As usual, common hardware and common drivers and free software components are easier to deal with. Try to do the minimum of effort possible that covers your integration needs. So use a pre-existing browser or pre-existing library that lets you do a browser, etc. Do roll your own if you need, that's fine, but try to avoid it. Prefer integrating directly with WebKit instead of having round trips to a local web server, and design your QA for also testing WebKit updates. Well, you would test updates for the whole system. It's part of your firmware, let's say. You should test it as well. And that's, I think, the main points I want to make with this. So I think we have maybe a minute or two for questions.
Hi, so one of the pain points people have when they are developing web applications is sometimes they are pulling like 100 node packages that might have compatibility issues with certain versions of rendering engines, right? So can you talk a little bit about the tools that are available for people that are developing web applications to use when they have those kind of problems?
Yes. So the question is about complex web applications and how to test them and debug them using an embedded browser, in this case, WebKit-based. I think the main web developer tool that there is the Web Inspector. It's similar to the built-in Web Inspector in a desktop browser, with the difference that it's a remote Web Inspector. So you may be running your web view or your web browser in some device, and instead of directly checking on the screen of the device because maybe it's small, or maybe it doesn't even have a screen, it could be a headless device, you connect remotely to it and you load the Web Inspector interface in your laptop and connect to the device, and then you can check your web application, like edit the CSS, check how's the DOM tree, like all the usual features of a Web Inspector. You can find them in the remote Web Inspector. It's a little bit tricky from the point of view that it requires a WebKit-based browser on the machine that connects to the remote inspector. Do we have support recently, well, since a year ago, to load it over HTTP? And last time I checked, it mostly worked in Firefox and it works fine in Chromium, so you can also use Chromium typically to connect to the remote Web Inspector over HTTP. There is, yeah, I think that would be the main debugging aid for web developers.
You know, I'll add to that I've used Safari for the remote debugging, and it works against COG. You mentioned a couple of different ways to integrate with the device. I've been using WebSockets on localhost because that allows me to push information from the device to the browser. Of the alternatives that you suggest, which is the simplest? Like, I don't think you could probably do that with the URI schema handler, or could you push through that?
I think it depends on, the question is, if one is using WebSockets in a local server to push events to the web content, if one wants to avoid the local server, what's the best option? So I think it depends on the kind of events. I would probably try to, in general, I think I would try to do it in my browser, which maybe reuses the COG library, to pick those events from native code. And how would I say? and that the JavaScript subscribes to them using EOSS messages. So it gets a promise, and whenever there is an event, the promise gets resolved. That's probably the easiest in this case.
Is the user script messages method.
Yeah.
Okay.
If the overhead of the IPC between the two processes is still too much, because it's going to be, I think it's going to be a bit, in general, it's going to be a bit better than going through WebSockets and wrapping through an extra protocol and so on. But if it would be not fast enough, you could also do it with the JavaScript Core API. But at that point, maybe the complication is not worth it. Yeah. I think it depends a bit. Okay. If you need the performance and maybe you want to avoid the memory usage of the local web server. WebSockets, if one has to once or ends up using a local server, WebSocket is probably the fastest from the point of view of minimizing latency anyway. So it's hard to say that there's a solution that will work in every case. I think I would probably use script messages for this kind of case if performance is good enough. Yeah.
Thank you.
You cannot answer this if you want, because I feel like it may be kind of stepping into the other talk you guys are giving today on doing testing. But when you're talking about like platform or picking the right hardware and getting your platform established to run WebKit on it, do you have any good recommendations as far as how to like verify that all like browser functionality is working? Because I mean, we've ran into issues where it's like, yeah, I mean, everything works, but then when you interact with the touchscreen, like, slider doesn't work, and so.
Okay, so for hardware, how's a good way to verify that all the features work? I would like to have a good answer that says, use this and it works, and you can test everything. I don't think there is like a definitive answer to that. I would say if it's something common, that is common hardware that maybe we test regularly, like what we use the most is IMX platforms, or quite often Raspberry Pi or similar. So this kind of system on chips, which are really common, usually things work. I think the tricky point, like you said, is with touch input, because there's lots of different kinds of touch panels people can use with the same basic system chip. And we have had regressions with touch input at some point in some major release, which then got fixed, but there's still some bias, that's true. I think probably the best way is to think which kind of interactions you need in your applications. Like, I need a pinch, I'm sure going to use a scroll, I'm going to use, etc. Design some simple HTML only, very basic thing that you can simulate the touch input with using WebDriver, and maybe test it with that if you want to keep it then later for the continuous integration. But I cannot think of anything that is pre-made that you could directly use. Maybe I don't know it, but at least I'm not aware.
Yeah, the WebDriver stuff sounds really interesting. I'm looking forward to that talk later today. Or tomorrow.
Yeah.
Sorry.
Yeah, and I think it's the end of my time. It's 50 past, yes. I wouldn't want to steal time from the next speaker. So thank you everybody for coming, and if you have anything else you may want to ask, discuss, tell us, we're going to be upstairs in the expositors room in the 5th floor. Thank you. A veces parecía que se quedaba como en suspensión, en plan stand-by, pero darle un par de veces al botón volvía. Por eso a veces fui atrás y delante un par de veces. Pero sí, funciona bien. Ah, no, it's okay. No. The microphone.
1, 2, 1, 2. So I think it's time. It's not working. Hello, I'm happy to be here. Thank you for coming. It's the first time I'm presenting, so I'll try my best. The subject of today is adding support for PoE in Linux mainly. I'm Cory Vincent. I work at Botlane, which is a company of consulting company of expertise in Belgium, Octo, on the Linux kernel development, and we have a strong focus on open source. And I'm currently living in Toulouse. The agenda of this talk is first an introduction to Power over Ethernet. So the principle, the advantage, the standards, of course, the hardware description, the power sourcing equipment basic processes, and the classification and the class detection. In a second part, I will talk about the support in PoE in Linux. So what's existing, the Netlink UI API I have added, and device binding, and why we decide to use the regulator API inside our PSC API. And finally, I will talk about the future features in the pipeline. So what is Power over Ethernet? The aim of Power over Ethernet is to remove the power cable, so to have only one Ethernet cable that will do do the data exchange and the power capabilities. So some of the devices that are interesting in this PoE is like this one, so a phone, a camera, or a router. And PoE can be applied over 2 or 3 or 4 pair for more power. The advantage of PoE is, of course, no more electrician. Don't need to be an informatician and plug the Ethernet cable. So it's simple and flexible. There is no external power supply needed, so no electrical certification. And of course, it's easy to reset all the power device as you have the hand on the power PoE controller. So the standards. First it was introduced in clause 33 in 2003 with 15 watts, the power up to 15 watts. Then in 2009 it's the power up to 25 watts with more type and class devices. This clause 33 describes only the PoE 2 standards. It was first, there is a name change in the standards. It is important because it induces a choice in the Linux development. So it was initially named Power via Media Dependent Interface, and then in 2022, Power over Ethernet. So the usual name that we use. And in 2018, clause 145 appeared for power over 4 Ethernet pairs, which allows power up to 71 watts and add more type on class devices. On hardware description, so it's a simple power source that apply source current on one pair and a return current on the other pair. And it will do for 2 pairs if in case of PoE 4. As Ethernet are designed to work over long distance, if the data and the power is on the same pair, we usually use isolation transformer to avoid any disturbance on the data. On the device side, it's called power devices. The aim of the device is to support whatever configuration that is plugged on the device from the PAC. So there is a diode bridge to allow whatever sense plugged on whatever polarity. There is possible for single or dual signature if the outputs are combined or separate, but it's mostly combined. I don't talk about dual signature. I really don't see it for now. On the PoE standard, there's naming, power interface naming, which is likely the RG45 port. It's just another naming for on the PoE side. So, as you might know, RG45 is 8 connectors, which means 4 pairs, and there is 2 possible cable, straight through or crossover, which means there is different polarity choice. Sorry. So here is a table with. If I can put in the line. So here is a table with the alternative A or alternative B pinut configuration for the pairs. So in all alternative A, the pair set use are 1, 2, 3, and 6, and alternative B are 4, 5, 7, and 8. So it's only on the PoE2 case, because on PoE4, of course, all the pairs are used. On the device side, it's not alternative naming, but it's mode A, mode B. On the MDEX or BX is when for the crossover cable, also when the polarity is ended. What is the power sourcing equipment basic processes and constraints? So when you plugged an extended device, you have to discriminate if it's a power device or not to not burn it, of course. So you have to assess the basic power equipment, the conduct, the mutual discovery, and the power negotiation. Often, when a device starts, it has a surge power, so the PAC should be able to support it. At runtime, a device could have peak power, so of course the controller should support it. There is also LLPD support, which I won't talk about it because it's not used for now, and it's really to modify the PoE configuration at the runtime. But for now, it's just it's a simple detection, so it can work without it. So we have to react in case of a PD drawing more power than it should. And also we have to support unbalanced load currents and limit the maximum power that are drawn. And in case of when the device is unplugged, we have to remove the power quickly enough to not burn another device that is plugged just after. So the automatic detection is made through register detection. The PSC will made a few pulse, and we detect the register detection of the rising edge of this pulse. And according to this detection, it can detect if it's a power device or not. Then we do classification. So know the power that the device is asking, and so which class to use. So it uses also pulse events, which is named class events, with more voltage, so 15 to 20 volt. And it measures the current draw variation on this pulse. And there is also on type 3 or 4 device there is a first long pulse which is called long class event, long first class event. Here is a table of the different class detected according to the pulses. So one class from 1 to 4 are detected with only 2 pulses. Then class 5 to 8 need the 5 pulses, or 1 long first class event and 3 more pulses. And with these, and there is also class for dual signature, but as I said, it's not used anymore, but not really used for now. With this class, there is power capabilities. So the default one is the 15 watt for the class 0. Yeah. And then it can up to 15 in class 3, and the maximum is so 99 on the PSC side, 99 watts, and so which means 71 watts on the power device side. So as you can see on the left, though, you have to check the controller to know if they are compatible to the which standard. If it's a more recent standard, which is this one, AO23BT, so you are able to support class 5 to 8, but it's not, you won't be able to support it. Now let's talk about the software side. So what's existing? For now, there is each PSC constructor have maybe its own code. So there is also a POED tool for switch that Joint Projects provide for the DentOS OS. So this tool is written in Python, and so we need to install Python. On Switch, it's not really important, but on embedded device, we might not want to install it. And also, it supports only one PSC controller. So don't ask us through a call for proposal to support the PoE in Linux. So I also work on another controller to have another point of view of what's existing. A TI, so on their side there is only a simple sample of code. So it's the same, you have to rewrite on your side, and it's not well written, a lot of comments with I don't understand why. On the Linux side, there was already PODL that was merged in 20 and 22, thanks to Alexei Jampel. PODL is power over data line, so it's kind of PoE but for single pair Ethernet. So there is a lot of similar thing that I will use for PoE. I have used for PoE, the core, the EIPA, or the S-tool PODL support, and it already have one regulator, simple regulator, PODL regulator support. But the thing is that PODL is only using one pair, so there is no such information as polarity pair sets, which there is in PoE. So only use PODL wasn't possible. So for now, I have sent the 9th version this morning, and there is already 3 patch of this series that is merged, thanks to Jakub. And the series I have sent, so as I said, comport 2 driver, one for the microchip one and the TI one. So let's look a bit on the code. So it's quite similar as PODL, as it's just report the standard on the S-tool netlink API. So there is control on status. So yeah, because for now on the core only the basic are implemented, so just know what the state of the PSC controller and the possibility to enable or disable it. On the device tree binding, as I said, there is not much information, so only the PSC port number is needed. So as you can see, here is a description of the PODL controller, and only the fundal to the PSC controller with the number of the port is used for PODL, and this is merged mainline. But on my side, on the PoE side, sorry, there is much more information. So I have to add a PSC PI subnode, which describe the PI, the power interface. As I said, it's like the RT45, but for PoE standards. So it describes the player set use. So for example, in the Pi 0, it's a PoE4 as there is a 2 per set use. This per set is relative to the channel of the PSC. And there is the polarity supported by the controller. A controller can support several polarity. It depends. So here is an example. And then on the fee side, it will use the same PSCS parameter as PODL to be like PODL and not do really something different. So in this case, there is no second parameter to take the port, as all the information will be in the PSC PI node. On the development, we decided to use the regulator API. It was an idea of Oleg's example, which is great because PSC is like a regulator but for Ethernet devices. So it's apply power to a device. So yeah, it's really kind of regulator. But the inconvenience is that it adds code complexity, so I have to use wrapper between the PSC world to the regulator world. But the benefits are several. You can use the already existing API of the regulator, like power limit, voltage status, temperature limits on CFS description. And also there is some features from PoE that can be interesting for a regulator. So like power priority. So if a controller have its current available decreasing, he have to shut down several ports. So he have to know which port have higher priority and which port are lower priority. So which port he can shut down first. And this could also interest the regulator API in the Linux side. Some code more. So just how we register the regulators. One regulator is registered for every power interface of the PoE. So just, I think it's a regulator of voltage and not current here. So yeah, the basic information of regulator to have it work simple, and we just register it, sorry, and put it in the PI structure. Then when the fee will get the regulator, so the PoE port, it will call the regulator get exclusive to get the regulator. So as I said, it's really wrapper to call the regulator API inside the PoE API. And it will check if the regulator is enabled or not and save it in a variable. I will talk. So this variable is important because the regulator API have a a way to do the thing, and it's not applied to a PSE. For example, if we get several times one regulator, it will just increase the counter, and if we put one time the regulator, it will just decrease the counter one time, but it won't shut down the regulator. On the PSE side, we just want, if we get several time, if we want to enable several time one port, it just does nothing, and if we disable one time the port, it should disable it and not look at the counter to know if it can disable it. So yeah, I have to put an intermediate admit state enable, as you can see here, variable to grab it and make it working. So what's next? With this development, there is currently several drawbacks. So currently, as is made with PODL development, the power interface is get from the fee, which shouldn't be the case, because in reality, the PoE is only wired to the RG45 port, so the fee don't know about the PoE on if it's present or no. It's not related to the PSE. As it is the fee that gets the PSE power interface, there is no way to get it from a network interface card driver. So when there is often in the switch driver, it don't register the PHY. So it's not possible to get the PSCP as it is done in the PHY core API. Also, something is odd. The power interface is the regulator provider and consumer. It works, but it should not be the case. It's not really good to have the same provider and the same consumer. So when we will have an Ethernet port abstraction in Linux, the consumer will be the port abstraction and the PSE PI is the regulator provider. And Maxime, my colleague, is currently working on port extraction, so maybe we will talk about it in ELC in Vienna. I don't know. Also, the next feature of PoE that is in the, I forget the expression, that will happen if the basic are accepted. So it's the possibility to set and read the power limit, the voltage status, read the class, the failure reason, configure the power purity, as I said before, so to shut down, which port to shut down if the available power is decreasing. And also a way to write persistent configuration, so a reboot of a board shouldn't, we may want to keep the same PoE configuration when the reboot happens. So demo time, it's not a real video, it's a video to avoid anything that goes wrong. I think if I did this, it's of course working. Okay, I can show it. No, it's not seen on my screen, so yeah. So here is the switch I worked on, which have the microchip controller. There is a device that measures the voltage and the power of the PoE, and there is a camera that will be plugged to check that all is working well. So here is a netlink stool command using the yn function, not function, but script. So for now the port is shut down. If I run PSE get, we will have the information that the port is off, and the admin state is set to true, which means the port is off in the UAPA. Then we want to to turn on the PoE port, so we use PSC set with the right admin control value. So we can see that the voltage is now on. There is no current, neither power, because nothing is plugged on the PoE. So if I plugged, no, for now I just read the information of what's the state of the port. So we can see that there is a class detected. The admin state is now state to 3, which means it's on. There is also power limit, so it will be in the future patch series. And also some status message, which also will be in the future patch series. Then if I plug the camera, of course the power will increase and we will see voltage and current on the measurement tool. And if I get the information from the PSC controller, you can see that the power is have increased, and that's all. Yeah, that's all. And then we can just turn off the PoE port with PSC set and admin control to value of 2, and it will turn off all the device. So video works well. I load my and so here is the reference, and all this work is sponsored by Done Projects. So it's thanks to them that we can adding support for PoE in Linux. Thank you for listening. So if you have questions or comments, I'm not really fluent in English, I'm trying to, but if you can ask really loud and clear, it will help me. I don't know, what time is it? Maybe you are hungry, so that's why you don't want us. There's one? Oh, yeah. It's okay.
Out of curiosity.
It's working? Nope.
Not on?
Maybe turn in.
Okay. There. Okay. This kind of stupid question, but compared to like the data lines, why is PoE such a comparatively higher voltage?
I don't know. Maybe we'll to have more power. I don't know. I don't really know. We don't try to invent. Ah, okay.
So yeah, you have to have a pretty high voltage in PoE, because as you are doing something like 50 meters and so on, the voltage will decrease, and so we have you will have less power to power your device. So the current will be too much if you have a lesser voltage.
So great talk. I'm
Thank you.
super stoked to see this in the kernel. I have a couple of questions though. You mentioned, and sorry if you mentioned this or it was implied, I missed it. You mentioned an integration with the PHY driver core. Does that mean that when you turn off the PHY, the Ethernet power goes away as well, or are those independent?
For now, I think if we turn out if the PHY driver gets down, it will turn off the...
Yeah, that makes sense. It's also really cool. It's integrated with regulator framework. That's good. Your port power priorities in the future, are you planning on adding that support via a Netlink API or via ETH tool or something different?
I think Netlink API is
Yeah,
the
for
right
sure.
choice.
For sure. I'll be interested to see how you solve the like port identification and how that looks. But yeah, we should talk more. And then the last question is there's a third PoE chip from Linear, the LTC 4266, I think.
Don't know.
It's okay, cool.
But if
Well,
you-
I'll look up your work when it's merged, which it's looking pretty good.
Okay, thank you.
And maybe add support for that chipset as soon as I can find a public posting of the data sheet, which, you know, is the blocking thing at the moment. But yeah, awesome, good work, thanks.
Thank you. Yeah, if you have more information of this controller, maybe it could help because there is only two and see how other things I made, so it could help for the development.
Yeah, for sure. It's just a AF controller, so just the first, or no, sorry, it does type 2 up to the 30 watt or 25 watt.
Okay.
But yeah, it's old, but still.
Yeah.
So that's why the data sheet should be available at any time. But yeah, cool. It's good work.
Thank you.
In your demo, you used YNL. Do you have like patches for ETH tool to make it like more?
Yeah, patches are already done. I think it's on my GitHub, and I will push it to still when the basic will be accepted in main Linux.
Okay, all right, thanks.
No more question. So I think I will let you go to lunch. Thank you.
Hello? Hello?
Yep, sounds good. Can I raise it up a little bit?
Yeah. Hello?
And then this, I'll get your mic in 1 second. This microphone, you can use it for Q&A, or you can repeat the question because it's being recorded and live streamed, and there's that little switch at the bottom there. And there's no audio. Hello?
Okay, I think we can get started. So thanks for joining. Good afternoon, everyone. So me and Soumya are here to present about the topic display sharing in heterogeneous systems using Linux. So we both are from TI. At TI, we have strong commitment to open source and an upstream first approach. So we both work at Texas Instruments as embedded developer, and so this is the outline of our presentation. So we'll go through introduction, like what we mean by display sharing, what are different practical applications of display sharing, and what are the design considerations and what different sub problems we need to solve to achieve this functionality. Then we'll go through different approaches to solve this problem, and like some of the approaches are already there in some vendor specific repositories, and some we are working on it. So we'll go through different possible approaches, then we'll show a demo of what we have done for this in our hardware, and then we'll stop for the question and answers. So what is display sharing? So nowadays in system on chips, we have heterogeneous systems where there are multiple processing cores, and you may want to control the same display controller from different processing entities, because you have like one display controller and more than one processing cores, like you can have an application or an ARM core and MCU core, and you may want to access the display controller simultaneously from both the cores. And for example, in this diagram, I'm showing that there is an MPU, and which wants to render the graphics using the GPU, and it wants to control the display controller. And you also have another microcontroller which wants to display the safety context using the same display controller and feed it to the same display. So why is this required? Like why not have only one core control both the graphics and safety or any all the feeds? Why not one core? We allow only one core to that, right? So this required because RTOS have their own unique capability. Like RTOS controlled displays are fast, and they are able to render low latency graphics in real time, and RTOS mostly lack the capability of GPU programming, so you cannot use or you cannot leverage GPU to render the graphics. And similarly, the MPUs or the application processors in Linux, we have GPU drivers already available, so we can use those application processors to render the GPU rendered graphics. And one more reason is like you want to isolate the display, right? For example, you have the safety context. By safety context, I mean like any critical display information that, for example, you have safety telltales in your automotive or any critical parameters. So you don't want to get that display context corrupted by the core which is running high level OS. So for example, your Linux or any other operating system which is rendering the graphics, it suddenly crashes. We don't want to impact the safety context that is rendered by the MCU. So there are different practical applications to it. For example, there is an automotive use case. In this, I am showing there is an IVI which needs to be rendered from the application core. And similarly, in display cluster, you will have like part of the display which is GPU rendered, and the other part like safety telltales and critical signs rendered from the RTOS. And similarly, in industrial HMI, there are critical machine statistics or any environmental parameters. You may want to render it from the safety context using RTOS, and the other part of the application you may want to GPU render it. Similarly, for the medical instruments, you may want to show critical or vital health parameters using the RTOS, and the rest of the GUI you may want to again use GPU to render that. And there is a possibility also that there could be multiple display panels getting used in your use case like IVI plus display cluster, and you have only single display controller. So these are the different applications where the display sharing will be useful. So okay, we want to achieve the display sharing, then what problems we want to solve, right? So right now if we look at the architecture, let's say you have Linux, you will have a DRM KMS compliant driver that is present. So it will try to take full control of the display controller. It doesn't know about sharing. So you cannot partition the resources directly using your DRM KMS driver. Similarly, your existing RTOS application, it will also try to take full control of the display. So both are in their own world, so they don't know about display sharing, right? So we want to define some handshake mechanism or some partitioning way to define this display sharing. And it's a generic problem. Right now each vendors, they have their own solutions and they all are solving the same problem in different ways. So if you have to achieve this use case, there are different sub-problems that we need to solve. Like we need to define like which core will initialize the display first, and how this information will be shared to the other core that the display is initialized. Then we will have to define some mechanism to partition the display resources, like which part of the display controller or which display resources will be owned by which core. And all this we have to do, and we have to make sure that there is no change to existing display windowing mechanisms or display servers. Like you don't want to change Western to achieve this use case, right? All your existing display application should still work seamlessly. Also, if you have like some specific part of the solution may depend on your display controller also, like if you have some specific features in your display controller, then you may want to design the solution accordingly. So we explored different approaches to solve this problem. So there were like two classes of these approaches. One was the IPC based. By IPC I mean the inter-processor communication between the two cores, and the other was non-IPC based that we did to achieve this. So both of these solutions, like there is an RP message K-Drive, it's hyperlinked. So this we did at TI some years back, and this not in upstream. And we also referred one solution for RPI, which was exactly not display sharing, but it could have still been, we could have still leveraged it for display sharing. So for the non-IPC based solution, we have posted an RFC, and I think it's going in the right direction. So what is the base design of the IPC based display sharing, right? So you have a display controller, it will have its own power domain or own clock domain and a register space. So in this design, we are giving authority to only one processing core to control power domain, clock domain and the register space. The other core won't have direct access to all to this display controller at all. The core which is controlling, having the control of this power domains and the register space will act as a display server. And the other core which wants to leverage or use this display controller, then it will need to act as a client and request specific resources from this server using IPC mechanism. So what all handshakes are required between the client and server to achieve this display sharing, right? So the display client will need to know from the display server, like when the display server has already initialized it. So we need a handshake for a display ready message. Then the client will also need to know what is the resolution or the mode that is set by the display server. Client will also need to know what are different resolutions supported by the display, and we also need a mechanism for the client to submit the frame buffer information to the server. And we also need mechanism to tell the client that frame done has happened or a vsync has happened. So there either needs to be an interrupt forwarding or HR timer based polling or dedicated IRQs. So all this we require because client, we have isolated the client completely from accessing the display controller resources directly. All this information it needs to get from the IPC mechanism. So first solution that we did some years back was that we introduced a new bus called RP Message K-Drive. So it was a device virtualization framework which provided different base APIs like how the driver can request different information and resources from the server and how it can receive the responses back. And on top of this RP Message K-Drive bus, we added another driver that is the remote device virtual display driver, which provided additional APIs to get display specific information from the server. And we use the RP message mechanism to talk to the RTOS firmware, and underneath we use the mailbox to notify the message transfer. And in the DRM KMS driver, we updated it to use these APIs to translate the upper level DRM KMS calls to this RP message APIs, and we added virtual encoder and virtual connector to enumerate this DRM components. So for this IPC mechanism, as I said, right, the client will need to know when is the display ready. So we added the ready callback in the probe, and we would defer the probe until the display server tells that it has initialized the display. Then in the mode set function, we are asking the remote core to get all the supported resolutions, and we are registering some callbacks which will get triggered when the remote core tells that the frame done has happened. Then for committing the frame buffer, we are calling the commit API from the RP message K-Drive display driver, and when the remote server has completed the frame done, this commit done callback will get triggered, and we'll get to know that the frame done has done. So we'll issue the vblank IRQ in the host. So all these callbacks that I showed in the previous slide, like ready, getrest, info, commit, we'll see how they are getting translated to the RP message. So all these are like in the ready callback, we are calling this API and we are sending an RP message using this message type. And for the getting the resolution, we have another message type, which again we are sending using the RP message K-Drive. And for the commit, we have this display commit function where again we are using the RP message K-Drive to send the request and get the response back. And for the commit done, as I shared in the previous slide, we are triggering the commit done callback from which we are sharing the vsync done info to the client. Then we also explored the Raspberry Pi solution to this. So Raspberry Pi had a fake KMS driver, firmware KMS driver, and their design was the firmware was in control of the display. So they were translating the DRM KMS calls to the RPI FKMS messages and controlling the display. So their architecture was like DRM KMS driver was there, and they were calling the mailbox APIs using the underlying mailbox driver, and they were like separate tags for each functionality, and they were sending the mailbox to pass on the request from the client to the server, and they were using a dedicated IRQs for this. So again, for powering up the display, they had a separate mailbox tag which they were triggering using this API. For getting the display config, they had a get display config tag, and for submitting the frame buffer or setting the plane, they had a structure which they were filling with this set plane tag, and similar structure they had on the firmware side, and once they receive this 32-bit message, the same structure they were enumerating there by getting the address of this structure from the mailbox. And for setting the display mode, they had this set timing tag where they were enumerating all the requested mode information from the DRM KMS and sending it to the remote processor using the mailbox. So both of these were not upstream. So we were just thinking about like if we have to expand on these approaches, or like what are the pros and cons of these approaches, right? So the first one, that RP message K-Drive, it had introduced a new bus called RP message K-Drive. So we had thought at that time, if there are more than one sharing mechanisms like display network or other drivers which have similar problem of sharing the resources between two cores, then it might be useful. But another approach could have been like, if you don't want to add a new bus like RP message K-Drive, and instead of it, if you directly want to have a driver like RP message KMS driver, similar to RP message TTY, then that could also have been one approach, because it's simple, it's similar to RP message care or RP message TTY driver, where we just directly leverage the Vertio RP message framework. Another thought we had, like if we have to share some common ground between the display virtualization and display sharing use case, then we could have directly used the Vertio KMS approach, where Vertio KMS driver would sit directly on top of Vertio bus, and it would share common ground with display virtualization also. Display virtualization use case can also leverage this, and a similar thing is already done in Vertio GPU. And I had seen this Vertio console driver where they had also added remote device support to it. So they were using the Vertio console for both virtualization use cases and remote sharing use cases. Now I'll hand over to my colleague Soumya, who would walk over through the static design.
Hello everyone. I guess I'm audible.
Yes.
So let's see what is non-IPC based static partitioning. So what do you mean by static partitioning of display resources? Say for if each host that is present in your system can be compiled to support display resources that is controlled by it. But if you see, we do require some kind of hardware assistance. Say for in a display controller, you have for each of the components that are present in your display controller has separate register space, separate IRQ lines that each host can subscribe to. Then independently you control the display resources that are present in your display controller. There are various use cases associated with this also. Say for example, in your system, any host that boots early, okay, and has configured the global configuration for your DSS, then how does any other host that boots up late in your system is using the same initialized state as it is? So let's understand the static partitioning by taking an example. So what do I have here is the TI display subsystem. So if you see, there are multiple components inside this TI display subsystem. It's a multi-pipeline display controller. We have something called video pipeline here. There is video light pipeline. Then there are overlay managers, video ports, and all. So if you consider this video pipeline, it's nothing but a component that takes a frame input, does some processing. So you can map it to DRM planes. Similarly, there are overlay managers. This overlay managers is nothing but takes multiple planes as input, and then based on your selection, like single plane or dual plane, overlays together and gives a final output frame. So, and also the video port. The video port is nothing but timing generator part that generates the timing signals to control your display. So altogether, they make up to DRM CRTCs. Apart from this, there is panel where you see the output. So it maps to the DRM plane. So altogether, if you see, this TI display subsystem has some unique features with respect to, it has each of these components has a specific register space so that each host can subscribe to. apart from that, all these components that are present in the display controller has IRQs. These IRQs are all together, what you say, mapped together to do duplication, and you have two different spaces called common region spaces, where all these IRQ statuses and registers can be read to. And each component, whatever these components are, that video pipeline and all, they provide the IRQs, and there is duplication. So any of the hosts can subscribe to these separately and have an independent control. So as I said, so why these IRQs are necessary to be known? Because we need to know that each of the hosts that controls the display resources needs to know the wavelength interrupts, when has been the frame done and all. So if you have an isolation already present, like separate spaces, register spaces, then each of these hosts can subscribe into. Let's understand it more by taking a use case. Say for example, there are two hosts in your system, that is RTOS and Linux, and they subscribe to separate IRQ lines. And the blue things that you see here, so RTOS is controlling one of the DRM plane, the DRM CRTC, and complete towards the panel. And Linux is actually having only one control of DRM plane. Then how do we tell that, okay, Linux does not interrupt the context of RTOS, or does not go and override the register spaces that RTOS did write? So we have something called firewalling. So we firewall those register spaces that Linux can corrupt or go override it. So this way, we do protect anything that is being, written by RTOS early in the system and can be overwritten by Linux later. So also with this, even though when you do firewalling, then you provide read accesses. So why do we provide this read access? There's a benefit towards it, which we'll go understand later. Let's see how we do this starting partitioning in device tree. So we define two attributes, something called exclusive ownership attribute and shared mode attribute. So this exclusive ownership attribute is nothing but any display resource that is owned by a host has write access to it, so it has exclusive ownership. And there is something called shared mode attribute, which any resources, display resources that are present in your system can be shared with any other host or entity. So how do we relate these things to the different register regions that we have in our TI display subsystem? So as I said earlier, the display controller of TI has some unique features with respect to different IRQ lines that are duplicated, where each host can subscribe into. And there is a global configuration register that is also duplicated, where each host subscribes into and looks for the IRQ statuses, the wavelength interrupts and all. So any host, say for example, who comes up early in the system and does the global configuration, can take the exclusive ownership of this common region. Similarly for the video pipeline, so in any of the use cases, you at least require a plane to be controlled by any of the hosts, so you can take exclusive ownership of this region also. Similarly for the other two, there will be use cases where you will have there are multiple planes being controlled by different hosts, but at the end, the overlay manager overlays all together. So you can have a shared mode attribute or a full complete ownership to it. But there is one-to-one mapping between the video port and the overlay manager. So you either have a shared mode or a full exclusive ownership based on the use case that you have. With respect to how we define this thing in device tree, is we have some device tree bindings. So there is something called DSS shared mode, where we say that, okay, you have to enable display sharing mode, and which are the planes in control that is owned by the Linux, and which are the video ports that are being used for these video planes. And in case of any use case where there is a complete ownership of the video port also, the final output, then we have DSS shared mode own VP. And especially, I said, when you have to have independent control of the display resources, you need to know the VPlank interrupts and all. So there is this common region which Linux can subscribe into. So there are duplicate regions which Linux can subscribe into and know when frame done has happened. So Let's understand this with an use case. A typical use case this is, so you have an automotive display cluster use case where, say for example, one of the plane is being controlled by Linux and rest of the DRM plane, the CRTC, everything is done by RTOS. So how do you say that in the device tree? So we do have here a device tree snippet where you say for example, which of the video plane that the Linux owns, what's the Z order of that plane, and what is the VP that is being shared, does it own any VP or not, and all. Once you have all these things defined in the device tree, how do you translate these things into your driver? So in TI DSS driver, we have a global display structure that says about all the display resources that you have in the display controller. So there is a function that updates this display resources structure. It parses the device tree and then updates the whole resources table with respect to the shared mode or exclusive mode ownership. Another example, if you see, we have a full pipeline being owned by Linux. So this can be a use case where you have two display outputs. One output with completely controlled by the RTOS and is displaying something, and another is like Linux is displaying something. Then you have full ownership of the video port, the video pipe planes, and all the things. So you define it like, okay, in the device tree that what's the Z order of it, what's the plane it's being using, and that is a owned VP or not. And you can achieve different partitioning or tailoring schemes that you can have with this device tree approach. Next is the firewalling scheme. So why is this necessary? So for example, in a system where your RTOS is booting early and it has configured some of the display parameters like the screen size, the width of the panel and all, and Linux needs to just use one plane and give the output. So if you firewall it and then provide the read access, so Linux can just read the registers and know, okay, what is the screen size, the width and all. It is also necessary that, okay, there are some use cases with respect to automotive where you want that, okay, whatever the resources that are owned by the RTOS domain are running in a safety context, so you require full isolation. So firewalling comes to play in that picture. Next is why we took static partitioning. So we are trying to leverage the hardware features. It supports robust partitioning of display resources. So there is no interference between each other. Contexts are protected from each other. Allows parallel and independent control of display resources. And we have duplicated interrupts for each host. So each host can subscribe to any of the RQ lines and know the VBlank interrupts. Also, there is no processing overload because of IPC or processor context switch. And overall, you have a faster software development cycle. So here we have a demo that shows how, caching any high-level OS like Linux does not alter the context of display that is being done by RTOS. So if you see, the telltales here are being done by RTOS, and this is being rendered using GPU by Linux. I just crashed the Linux here using 6RQ, and if you see, the telltales are still rendering, but the high-level graphics stopped. We do have a demo at booth EDP3. Please come join us to know more about it. Here are the references that we have and we took to have this presentation. Thanks to Texas Instruments and Linux Foundation for giving us the opportunities to speak here. And we are open for Q&A.
Hello, thank you for the talk. How much of this work, and especially the device rebinding, has been accepted upstream?
It's posted. It's in RFC. Some comments were there, like they didn't want to have the DSS shared mode attribute. So some changes are there, and we'll work on that and post another version of the patch but it's mostly aligned to what I saw in the responses.
Right. And so if I understood well, your use case is sharing the display between two CPU cores. Have you also considered the use case where you need to share the display between the normal world and the secure world? In a case where you have one core and you need to run some secure payload that needs to access the display and also the normal world? Or is this not the use case that you have?
Yeah, that's the use case. So basically, the customers do require something like, in case of automotive display cluster, so each of the frames that is coming from MCU requires safety monitoring. Like, so you have freeze framing or the data integrity check of each of the frame. So that can be also done, and the MCU renders those frames and it has to check those things. So there is a complete isolation. And if high-level OS crashes or something and it doesn't, it freezes or something, then still the safety context.
Yeah, but this is with two cores, right? An MCU core and an MPU core. I was referring to, you have a single core like Cortex-A, and you have normal world and secure world on the same core, right? Like, yeah, exactly, Linux plus Opti or something like that running on the same core. Just wondering if it was also covered in your work or not.
So no, I don't think we are targeting that one.
So related to that security question, if the Linux core is like trying to get past the firewall to overwrite something else, how I believe I talked with you guys at the booth, and you said you actually have hardware to deal with this, but can you speak more of how it's firewalled? Does it only give a time slot to write just the right amount of memory, or could I pass something and overwrite my buffer and display? It's secure in an area. Like, could I pass a false message to the user?
So with respect to firewalling, so basically all these, any of the display resources, say for example, these pipelines or anything has a register space, right? So we do some kind of firewalling with respect to foreground and background firewalling that we do at NTI parts. So you have a common region that you allow some core to have access to, and then on top of that you give foreground layers that which other cores cannot have access specific to it. So if you have that, then there is a special security manager that gets exceptions, and you cannot write it at all. You cannot access it. It keeps on having exceptions.
Yeah, so if you look at the display controller we have, so we have like the display controller register space is organized in such a way that all the resources are partitioned in 4K boundary. So we have this support in the hardware, to support the firewalling feature, which the device manager can leverage to firewall specific register spaces from the other cores.
So when you're partitioning, are you partitioning pieces of the window? Is that what you're doing? Or is there a way to overlay on top of each other? I see the overlay manager in the static one. So if I want some of my safety critical on top of maybe a video, it's in the mouse?
Okay. Yeah. So this is a plane. This is one plane. You can assume it as one plane, and this is another plane. Both of them are submerged together with a background by this overlay manager, and finally given an output. So if you do anything here in this plane, that's fully isolated. If you do anything with this plane, it's fully isolated. Both of them take input separately.
Okay. And then there's, I guess, the overlay managers where you manage what sits on top
Yeah,
of the
you
other
can
one?
you do blending, you can do transparency and all kind of stuff.
It's like a video mixer, like it will mix the video pipeline and video light pipeline. And
So using the IPC with the RP MSG, does that add latency or any other performance hit compared with just going straight from Linux out to the display?
I think there might be some delays. We didn't prototype it because we had some hardware feature to leverage for this. So hardware was updated to support this kind of use cases. So we tried to leverage that with static partitioning scheme. But I would say IPC also has its own beauty, and this also has its own use cases. For example, if let's say you have some use case where the remote core changes the resolution on the fly, now how do you communicate it to the Linux? So that we need again to define something for that, right? Even with what IPC mechanisms we had, we didn't have a good handshake for these kind of dynamic changes. So this static partitioning scheme is good for like you have one core, it initializes it with the max resolution and you stay with that resolution throughout.
Okay, thank you.
Thank you.
So I guess there is a complete boot video. If you want to see, we can show it like so. So this is the RTOS that does the splash and immediately keeps the display up with telltales being rendered. And in the background, Linux did boot and just launched another plane.
Yeah, is there any mechanism to sync frames if there's any sort of requirements around that?
Sync frames with respect.
Right. So if you have two different pipelines, is there a mechanism to sync the frames if someone has that requirement?
So that's what the beauty of this overlay manager that we have in the display controller. We have separate register spaces where the duplicate status are already present. Okay. So if I say one pipeline has done a frame done and it's being out, the same status can be seen by the other host also in a different register space. Okay. So both the hosts are knowing at the same time when I am doing a frame done. So you have no latency, you have the same FPS that you can achieve.
So there are dedicated interrupts to each host, and the hardware supports asynchronous updates from different hosts, and with it guarantees the frame done happens. The interrupts are triggered at the same time. So that's
okay. Thank you.
Hi, is this available on the TDA4AP family?
It's a similar display controller. This one is 62P, which has DSS. Similar DSS, not exact, but similar DSS. So this solution can be leveraged on all the TI K3 based TI devices, including what you said, the TDA4.
Okay, thank you very much.
Thank you. So I think TDA family, Jacinto family has even more common regions, so that you can support even more processors, more than 2 processors also.
I can leverage multi-pipeline, multi-output scenarios with respect to that. Like four hosts can keep on controlling parallelly 4 displays, 3 displays, 2 displays, like that.
So presumably a real-time operating system is not supposed to crash, but if it does crash, will it still display what was last shown, or will it go to nothing? Because like when I saw the Linux crash, whatever was shown last stays up there, and I don't want to give my user a false something. I'd rather an error message show up.
So we do have specific features with respect to the TI display controller, like detecting freeze frame and data integrity check. So, and as I said, like these IRQ lines are duplicated and present to each of the host. So any MCU core that is running in a safety context can also subscribe to this IRQ and do safety monitoring. It can keep on getting those interrupts of when freeze happened or when you have a data integrity failure of the frame. And it can do some diagnostics and do a blanking of the display, restart the display, save the context, all can be done.
Okay, I think we are done with the time.
Yeah.
And if no further questions, then we can close.
Thank you.
Okay, thank you.
My problem is that my operating system is starting up too slow. Okay. So this doesn't meet the requirement because the user then has blank screen, and we do have problem with that. And exactly that. And this would be exactly the perfect solution for that.
Yeah, we did achieve it on AIM-62P device, or Citara AIM-62P device, but in this scale across platforms, whatever we have done in AIM-62P. If you want to have a contact, let's meet at the booth.
Yeah, I come to the booth, and then just I need to check with my other colleagues that are really working on that, but I would propose this solution to them because
we can discuss the full architecture.
guys hear me? Is it working? Can you hear me? How about now? Yeah. You want to do the job of mic runner? Thanks.
Hello.
Okay, can you guys hear me? Cool. It's 2:55. Let's get started. So welcome to my talk today on engineering secure SSH access for engineers. My name is Colin McAllister. I'm a software engineer at Garmin. My duties there are mainly to assist in developing the distros we use on our marine products. So for those that don't know, Garmin makes a very wide range of marine products, going from chart plotters, which are the glass like multi-touch displays, to like radars, sonars. A lot of that runs on Linux, so it's really exciting to work there. I've worked with embedded Linux for about 6 years. Fell in love with it in college while working as an intern and have wanted to work on it ever since. Whenever I can, I like trying to contribute back to open source. You'll see my name sometimes in patches on Open Embedded, Yocto meta layers. It seems like it's cutting in and out. SW update and HVAC. And so whenever I'm not programming, you'll generally find me on a bicycle, preferably not on pavement. So a bit of a disclaimer here before we get started. I'm not a dedicated cybersecurity professional. I'm a software developer. Cybersecurity is kind of one of my side passions. And so at Garmin, I did a lot of work on SSH for marine products, and so that required a decent amount of research there. And so I kind of wanted to take what I learned and share it back with the community. We don't really, unfortunately, have enough time to really dive into the details of how every single SSH authentication method works today. So really, I want to focus on discussing each of the methods and how they comparatively meet the demands of embedded Linux. Lastly, just to explicitly say it, the views expressed within this presentation are those of mine, and they do not necessarily reflect the views of Garmin. So why are we here today? Why am I talking about SSH authentication? Because security is really important. I think we all really enjoyed Marta's talk yesterday talking about pretty serious issues that can happen whenever you have security issues with embedded Linux products. Embedded devices often have a very physical presence. They can be used in industrial, automotive, marine, medical, and potentially other areas. And so that can sometimes come with a possible direct impact on user safety. So, even if you're not making products in a critical sector, conference room monitors and like baby monitors, we all remember the stories back in the day about those being hacked when the first Wi-Fi baby monitors came out. So, we're all kind of aware security is important. Governments are really starting to step in and regulate that as well. You see that in the EU Radio Equipment Directive that's coming down the pipeline for next year, and the newly minted US Cyber Trust Mark. So let's take a step back. Since this is a beginner presentation, I just wanted to quickly explain what SSH is. SSH is the secure shell. It's a protocol to be able to gain secure connections and authenticate connections over potentially insecure networks. So SSH is built on top of TCP/IP, and it can be served as a foundation for a whole bunch of stuff. I have with me a 700-page book on how to use SSH. It's a pretty easy thing to work with initially, but I think the 700 pages speak for themselves on what you can do with it. There's a couple other benefits too as far as compression as well. I'm sorry about the slides here. So SSH is a Swiss Army knife for developers. With it, you can gain remote shell access, tunneling, port forwarding, be able to transfer files to and from devices, and even do things like X11 forwarding, if people still use X11. And so all that can be done over an encrypted and authenticated connection. So, with this, it's a really powerful option for developers to use with their devices. As far as authentication goes, SSHD, the daemon that runs on the host, supports multiple ways for clients to authenticate. Authentication methods can be enabled, disabled, configured, all that within the SSHD configuration file, which is located in etc SSH. You will need root level permissions to edit this file, and it generally comes with default authentication configurations. So make sure you kind of know what those are whenever you're modifying those. So SSH with embedded devices. This is typically, from my perspective, how a lot of developers typically interact with embedded devices. You know, a lot of times, like this device over here, it doesn't just come with a display, and so there's SSH gives a really great way to get a shell on the device, work on it, diagnose issues, develop, so on and so forth. So in this case, SSH devices are the server we're talking about. Embedded Linux products may or may not have internet connectivity and correct system time. These are important things that we'll kind of continue to talk on as I go throughout the presentation. One last thing to note is that software updates may be difficult or not guaranteed to be timely. A lot of times it potentially requires users to install updates, which we all know how much people love doing that. So, what's the most secure solution? Just turn off SSH, right? You know, on your release builds, you can just turn off SSH. The most secure door is a brick wall. So this will eliminate any risk of third parties gaining access to your device over SSH. So I guess we all go home, right? I think that's not really a realistic solution for all of us. It may work for some people, but I think it limits the ability for your developers to interact with the builds that you're releasing to your customers, and also prevents any sort of field diagnostics or maintenance once your devices are deployed. So today we're going to really be talking about secure authentication methods that work with deployed devices. So before we start diving into authentication methods, let's kind of go over some of the requirements, you know, as far as what I was using when I was evaluating which products are good or bad. So a solution needs to be secure and limit access to only the approved individuals that you want to give access to. We need the solution to scale. You know, when you're talking about embedded devices, you're potentially talking about thousands of devices out in the field, or even more than that. So we need some way to be able to make a solution that works for every single one of those devices. And then lastly, I think, you know, these may not apply to everyone, but I like to think about edge cases. So, you know, authentication may be required without internet connectivity or correct system time. I mean, even if you have internet connectivity or a system clock, I mean, what happens if your real-time clock battery dies on your board? Or what if the modem goes bad? If you send a software engineer out to figure out what's wrong with your device, it's going to be a huge pain if they can't authenticate and gain SSH access. So, yeah, so we'll start with the first authentication method, password authentication. So this is the default authentication method. Anyone that's used SSH and didn't have a great or an authentication method already put in place, you'll get prompted for a password. What password do you enter? It's the password for the user that you intend to SSH in as. So in my little example there on the right, I'm SSHing into myself on my own PC, and since I don't have any other way to authenticate, it prompts me for a password. So for embedded passwords, or passwords on embedded Linux, there's really two ways we can think about this. We could do one shared password used across all devices, or we can configure each device with a unique password. The shared password across all devices is probably the easiest. You can bake it into your firmware, and it's updatable within your firmware updates. But if you have that password for some reason compromised, if someone in the field cracks it or some developer walks away with it, all your devices are compromised. Not really an ideal solution. For unique passwords, this gives you a lot more granularity where one password will only compromise one device. But I think that's a huge burden to maintain. You know, you'll need some sort of database that stores all the passwords. Let's say you make a unique password or unique random password for each of your devices, or maybe you can create some sort of password derivation function that takes publicly available information like the unit serial ID or the MAC address and hashes that into a password. How do you keep that password function secret? I assume if you wrote that code, it would get stored in version control. It's probably about as good as storing your passwords in version control. So not really an ideal solution there either. And so ultimately, like beyond that, I mean, you'll need some sort of way to be able to pull passwords down if they're stored in a database as well, which gets into our problem with internet connectivity, if some developers on the field trying to gain access to a device. And it's also just this isn't a really great way to automate authentication. There's really no built-in way to automatically enter a password with SSH. There's some tooling available, but I just wouldn't mess with it. So all that's to say, let's not use password authentication. Passwords can be cracked, and that can leave one or more of your devices compromised. We're actually starting to see regulation now that's also regulating people to not use globally shared passwords on their embedded IoT devices. So I wouldn't recommend using that. And then, so unique passwords are better, but I think they add way more complexity than they do security. It's just, I don't think it's a real great option there. And lastly, it's just hard to keep these passwords secret and automate password entry. Okay, so what's the next authentication method? I mean, as we kind of talk through these, I think to me it kind of follows my path on these authentication methods as I learn them. Throughout my career, public key authentication is a great one. It's generally what I think most people will do when they get tired of entering their password every time they use SSH. So with this method, it's a challenge response mechanism that's automated. So a server will send a client a challenge, and then the client will generate a response with their private key, which the server will then verify with a copy of the public key that's stored on the host device. Trusted public keys are stored in a text database file within the .ssh directory in the user's home directory that you're trying to SSH in as. With public key authentication, generally private keys will be harder to crack versus passwords. Unless you make really long, complicated passwords, that rule will stay true. But SSH users will need file system access to the private key that they use. That private key file is subject to exfiltration. A disgruntled employee could walk away with it. It could be left on the thumb drive that some developer leaves, out in the field when they're doing diagnostics work. It's easy to lose files. So, and especially when people are carrying them around and not necessarily storing them in a secure manner. And so then we also dive back into the same exact problem we had with password authentication, where it suffers the same shared versus unique problem. Do you trust all of or are you willing to risk all your devices using the same key pair and only have to worry about your developers using a single key? Or do you want to create some sort of database that stores a unique key pair for every single device that you create? Don't really like either of those. So I would also recommend against using public key authentication. Although it can be more secure than passwords and is more automatable, it suffers the same exact issues as passwords. Yeah. So now we'll start talking about some of the more stronger authentication methods that are built into OpenSSH. So the first one is GSS API, or most people know it as Kerberos, which is the most popular implementation of that protocol. This is a much more complex authentication mechanism than the previous two methods we just talked about, and involves several correspondences with where our client will first talk to an authentication server and then take a ticket from that device and pass it to the ticket granting service, which will then give the ultimate secrets that you need to authenticate with your intended device. So with this method, it's pretty well built because it all relies on symmetric keys between all your devices, and also it supports scaling pretty well. Anyone that's familiar with Active Directory and LDAP, that's basically Microsoft's implementation of Kerberos. And when we're talking about that being used in enterprise context with many devices, that kind of shows that this could be potentially used in an embedded context as well. But I think it's somewhat tricky to use in an embedded context. All devices and infrastructure require accurate time for this to work because tickets used in Kerberos are very time-based. And it also kind of touches on the same issues we talked about with password and keys, where it's difficult to manage unique keys for all your devices, especially on the edge, where internet connectivity may be spotty or not available at all. So while this is a strong authentication method, I don't think it's very easy to implement for embedded use cases. If someone can prove me wrong, I would love to hear it. Feel free to contact me. It'd be really interesting to see if this works. But today, what I really want to talk the most about is what I think is the strongest form of authentication, which is certificate-based authentication. So this is fairly similar to public-private key authentication, but instead of the device trusting the public-private key pair of the user, it ultimately trusts a certificate authority. And so whenever a client has their own key pair, they can sign their public key with the certificate authority's key pair, which will then generate a signed public key or certificate. It's basically the same thing. And then use that when authenticating. So whenever a user uses a private key that contains a certificate with it, the host will verify the authenticity of the certificate with both the CA's public key that's stored on the device and also the client's public-private key pair. Sorry for the technical difficulty, folks. Okay. So we've kind of talked a little bit about how certificate-based authentication works. Let's talk about the SSH certificate itself, or signed public key. So this is a certificate format that was specified within OpenSSH. If you go into the OpenSSH source code, there's a protocol.certkeys file that specifies this format. So essentially, it's a signed public key with some extra options. You have a validity period, like most other certificates, that specifies when the certificate is valid. You have critical options, which is a unique feature. And so these features are control features that restrict access. So the three that are kind of built in right now is force command, source address, and verify required. Force command is really cool. I think it has a lot of really cool use cases where you can specify a command that will be the only command that the certificate can run if authentication happens. So potentially if you have someone out in the field that you don't really trust to give them full SSH access, but you want them to just print out a log or give you some other diagnostic information, you could just specify what command you want to run with force command, and then when they try to SSH with that certificate, it'll just run that command and immediately exit. So pretty cool option there. Source address just limits what addresses clients can use when they're using the certificate. You can just specify a CIDR block within the certificate with that critical option. And then verify required, that's one that has to do with the biometric keys that are now used. I've never really used it, so I don't know a whole lot about it. But there's also extensions, and so that these enable features once access is granted. So these deal with like being able to permit X11 forwarding, port forwarding, a bunch of other features. The PTY one is useful if you are using something like force command, and you can turn that off so you can guarantee there's absolutely no way shell access will be granted with that certificate. And so there's a couple other ones too that are just kind of metadata items, like there's key ID, which is a great way to audit what certificates are being used on your devices because that will show up in the device's logs. A serial number for the certificate, and then principals is an important one. So because the certificate authority is globally configured in SSHD, certificates will essentially work for any user on that host device. So you have to specify what users a certificate is valid for. So like in this example on the right, the only principal is Colin, so that's the only user I can SSH in as with this certificate. So as far as the demo of just kind of showing how this works, like on a local PC, you can demonstrate this authentication flow fairly easily. So we'll need 2 key pairs before we proceed. So we'll first generate the certificate authority key pair and the client's key pair. These can be whatever format you want. And so then once we have those created, we need to add the CA's public key to the authorized, or to the SSHD config file. So trusted user CA keys is the option you want to specify, and then you specify a path to the public key on that host device. You can generally just throw those keys into etc SSH. And so once that's done and you reload SSHD, you should be good to go. The SSHD will now trust your certificate authority. So we need to get a certificate next. So SSH Keygen will do this for you. In a more actual deployment-based application, you probably want to do this within some sort of signing server, which we'll talk about in a couple slides. But this kind of helps demonstrate some of the options that you want to add whenever you're getting a certificate. So the first option with that keygen command is specifying what certificate authority private key you want to use. The next option is the identifier you want to add. So like I was saying with auditing, you probably want to specify maybe the developer's name or their username within that identifier. And then next we'll specify principals. So since this is an embedded device, we'll just go ahead and give them root for the principal and make it valid for 1 day. And then so lastly, we'll specify the public key of the that we want to sign with the certificate or the certificate authority. So once we have that, you'll now have a certificate file in the same directory. So SSH is kind of picky with how certificates are named. So you'll see after this operation, you'd see a client ID ECDSA hyphen cert.pub file. So that's your certificate. SSH is the client is also configured to look for a key or a certificate file with that naming format when you specify a key to use when calling SSH. So for this last option where we actually call SSH, you specify that you want to use a client ID ECDSA key, and it will find the associated certificate there and use that to be able to SSH into your device. So with all that kind of said and talking about how certificates work in principle, let's talk about embedded use cases. So as I was kind of saying previously in this presentation, time may not be reliable on your devices. If you have a system clock that's off and outside the bounds of your validity period, your certificate will fail to allow to authenticate you. So it's not that hard to patch OpenSSH to disable the validity period checking. I've included the lines from sshkey.c where that validity period is checked. So if you just comment out those lines, the validity period is no longer checked for certificates. For those kind of playing along, you'll probably think, wow, now certificates are really powerful because if you disable this, then a certificate will now and forever always be valid. So it really leaves the solution no better than public key authentication, and maybe even worse because you're now distributing a whole bunch of certificates and key pairs that will allow you to SSH into every single device. So there's a way to fix this. We can, with the cert keys protocol in OpenSSH, it specifies how developers can create their own critical options. So let's assume we have devices where we have a unique identifier built into the host name, or in some other way, we could be able to create a new critical option that specifies what unique identifier you want to authenticate with. So what we can do is be able to bind certificates to a single target device that you can SSH into. So for this example, I created a critical option called hostname@company.com. The @company.com is because inside the protocol, it states that you should always add your company's domain to any critical options that you decide to create. So we can patch SSHD to only accept certificates when the device identity matches what's specified in the critical option. So instead of binding certificates over a time-based domain, we are now binding certificates over a device identity domain. This could be used with or without validity period checking. If you were able to leave validity period checking enabled, you now have very tight access control with certificates, where a certificate's only valid for a certain period of time on a specific device. But if validity period is not possible on for your application, a certificate now has some sort of granularity that I think makes it better than any of the other options we've talked about so far. So how complicated is it to add a new critical option? Not too bad. So right here is the lines of code I wrote and added to OpenSSH to test out this idea of using the hostname @company.com. It just requires basically an extra case inside authoptions.c where it's checking the critical options of the certificate. So with that, all we have to do is just add an extra line to our SSH keygen command where we specify what critical option we want to use inside the certificate. So right here, I added my device 123 as the device that I want to include for my new critical option. So now my certificate will only authenticate with my device 123.local. So one really important thing to stress here is if you did something like this, if you do omit that critical option, a certificate's still going to work like on every single device because that critical option won't be used. So you'll need to have your signing server enforce the use of that critical option where every certificate contains that critical option. Otherwise, your signing server will be creating certificates that work on every single device. So all in all, let's summarize here with certificates. It's really easy to configure your host to trust a single certificate authority's public key. If you ever need to roll that due to some issue, you could do that in a firmware update very easily. So we get basically that same ease when we were talking about doing a common public-private key pair or a common password that's shared on all your devices. But the real strong strength of security here is we can lock away that certificate authority's private key and put it hopefully in like an HSM or some sort of security token in a server in a locked room in the middle of your corporate office behind a firewall. And so that way there's really the most minimal risk that this key could ever become compromised. Besides that, you can also push authentication to that signing step. So developers can use like LDAP credentials to authenticate with the certificate authority signing server. And that way you're then also auditing each signing operation where you know what users are asking for what certificates. You guys don't have to go design this yourself. There's several implementations that already exist out there for SSH certificate authorities. HashiCorp Vault's one that I'm very familiar with and would definitely recommend. I also know Small Steps SSH platform seems pretty good. Honestly, one of their white papers on using SSH certificates was what convinced me to explore this option a long time ago. So certificates can be very short-lived if you can guarantee time. So that's a really awesome perk here. So for use cases where validity periods can be used, you can give certificates like a one-day certificate. So every morning they log in and get a certificate, and they can use that for development. And then when they come in the next day, they just have to get a new one. Pretty easy there. The critical options and extensions can add a lot of flexibility and features that don't exist with any of these other authentication methods that we talked about. And it's not very hard to alter OpenSSH to work around potential embedded requirements that you have to make certificates work. So One other thing too is besides client certificates, which is all we've been talking about today, there's also host certificates for SSH, which is basically the same thing, except it's the host private keys are, the host public keys are signed with certificates as well. If anyone's familiar with SSH and how you'll initially be prompted to trust a public key for a device you're SSHing into for the first time, in the industry we call that TOFU, or trust on first use, and is one of the easiest ways for like a man-in-the-middle attack to happen. So if you create host-based certificates or host certificates for your devices, that provides a method for you to avoid that, where your clients can be configured to trust the certificate authority in their known host file, and that allows your clients to seamlessly authenticate without having to do that prompt and worry about man-in-the-middle attacks. So if none of these solutions today seem like they worked for your use cases, that's totally fine. The one other thing I want to talk about is PAM. So PAM stands for Pluggable Authentication Module. It's another utility that within Linux that allows for you to use PAM authentication modules, which a lot of them exist out there, like OAuth 2.0, Google Authenticator, YubiKey. And so you can specify within your PAM configuration files what you want SSHD to use, and then you can configure SSHD to use PAM authentication. So this is kind of the Wild West, and if any of you want to go out on your own adventure and explore some options there, feel free to do that. So with that, I want to thank everyone for their time. If you have any questions, I'll be happy to answer them. You can also reach out to me on GitHub or LinkedIn. And then lastly, I have a page of references for people to check out related to the information I shared on this presentation.
Hello? Are you using certificate revocation lists, like to? I know some devices don't have internet connectivity all the time, but maybe a way to sync downstream CRL to revoke the certificate. Let's say you have a certificate and that developer is not in the company anymore. You want to revoke. Do you have a way to do that?
I think there is work ongoing, if it's not recently done, to add like CRLs for SSH certificates. It's been something that historically hasn't been supported because like with X509 certificates or any of these other ones that have CRLs, we're generally talking about like several year-long certificates, right, for your website, where if, yeah, you have a compromise issue, you can throw out something you want to add to your CRL. Because SSH certificates are so short-lived, and that's how they've always been advocated to be short-lived, I don't think anyone's done the work to add CRL, but I swear I saw a patch not too long ago that was adding the possibility of a CRL for SSH certificates, but I don't know much more than that.
Thank you. So what would be kind of cool is if the SSH daemon would be able to interrogate the NTP client to find out whether it's synchronized and then fall back to the critical, what was it?
Critical options.
Critical option.
Yeah, I mean, the time issue is something that I've been wanting to do more work on. Like, I think one of the challenges that I spent a lot of time thinking about was, it's like, okay, you have a device that has incorrect system time. You know, how does that device get updated? Like because like I think about from my applications, right? We have boats that have GPS on them. So they should always be able to get correct time, but what happens if that's like in a garage, right? And so to me, NTP is obviously a solution there in some way that you could have NTP packets into it. For those that are familiar with NTP, there's no way in the default implementation for authenticity of those time packets to be verified. So that creates a challenge. But there are new emerging standards on time sharing that provide authentication. So, one of the ideas I had was like, what if you had some sort of, hardware token I could plug in my device as a software engineer going out in the field that is able to provide, secure authenticated time to a device to get it updated, and then you could use validity periods. There's some ideas there. I honestly haven't had the time to really engineer some sort of solution there, but maybe in a couple of years I'll give a presentation on that. We'll see.
So if we go with certificate-based authentication, what's needed to be done on our side as a company to prepare the image so that in case something goes wrong, for example, and we need to get from the customer some logs, and we have, let's say, 5 different customers, do you have to then prepare image each, so custom image tailored for a customer or not? And what's needed then, how would this look like in a real life?
Yeah, I mean, that's the easy answer is that's ultimately up to you. But to kind of explain out a potential use case, like if you have 5 different customers, right, you may want 5 different certificate authorities, one for each of your different customers. So
but
there's
that
isolation.
makes my life as a developer, difficult. That means 5 different images, built, and then in production they would have to flash 5 different images per customer. That's a no-go. Let's say.
But if that's the case, then why not just use one certificate authority for all those customers, right?
Okay, and then they say we have a problem, and we say, okay, send us the logs. What do we need to do? We have to send them. How would that then work?
So for internal use cases, you could have your developers just directly query the signing server to sign their keys. If it's someone that's outside of your company, what you can do, or what I would do, would be to create a custom key pair that's not used for anything else, generate a certificate for it. If you just need logs from the device, use that force command option to specify a command to query the logs like you want, and then zip all that up together, or tarball it, and ship it off to them with instructions on how to use SSH. And I mean, as I kind of was showing back in the original demo, I mean, ultimately, oops, went too far, sorry. All you have to do is just have them run, extract your compressed set of files, and then just run SSH with that command. Force command will run automatically. So, I mean, if you run this command with force command, the logs will be printed out. You get the logs from whoever runs the command, and that's all you would need.
And how would this, if the time is not correct on the device, if we say you have a certificate which is valid for 1 day, then how this works if the time is wrong on the device?
Yeah, then that's the challenge with certificates. If that is, I mean, you can either try to create a certificate that is wide enough in a validity period that it should capture the system clock being off, or if you want to account for that edge case, disable validity period in SSHD on your device, and then just make sure before you send them the information, you get some sort of device identifier of what device they're trying to get into, and use a critical option to specify that certificate can only be used with that singular device.
Okay, thanks.
Yep.
Can you have different CAs with different validity periods?
So the question is, can you have different CAs with different validity periods? Yes. So I've primarily worked with HashiCorp Vault for SSH certificate authority, and it's really easy to set up, multiple SSH certificate authority like engines within it, and each of those can be individually tailored. So you can have, maybe your trusted developers will get a 1-day certificate, but your field software engineer that's just debugging something out in the field gets 15 minutes to make that very short-lived, very minimal. And so you would just potentially, you can actually, even for the same certificate authority key pair, like in Vault, you can specify like different roles. And even with LDAP, be able to specify what roles what users can use. So, that's the thing is like you're really pushing all of that like authentication and like access control to the cloud with like Vault, where it's really easy to do that. And then all your devices have to do is just trust a certificate authority's public key, and that's all you have to do on the device. Well, I think, one more question, then I think we're out of time.
Oh, sorry, he was first. Sorry.
Two questions.
There were the 2 patches that you said for OpenSSH.
Yep.
Have you tried to send those upstream, or would those be, no, those are security? Like, yes. I imagine a compile time option to disable time might be a path.
I think that's one that will probably never be upstreamed.
Okay.
I would really like for it to be like a compile time option, but I would have a hard time believing that the maintainers would ever accept it. We did try pushing the host name or variant of the host name critical option upstream, and we're told by the OpenSSH maintainers that it was too niche of a use case for them to accept it. So for both of those patches, I have those on GitHub. That's what those links go to. It's on my OpenSSH fork on my GitHub. You feel free to look at it. I honestly feel like there's, if enough people ask for it and we find a solution that kind of works for everyone, the maintainers will kind of hopefully accept it at some point. But it was one of those things where we tried, failed, and then decided it's something we're okay accepting, to implement ourselves. So.
This probably reduces the attack surface of those password bots, which hit devices on networks. Are you using any other things like fail to ban to try to limit those botnets and stuff?
Yeah. So are you talking about with the signing server or with your edge devices?
The edge devices.
Yeah, I think that's, if not one of the most biggest reasons not to use the password or private key authentication is because as we have IoT devices now that are internet connected, I've seen plenty of DEF CON talks where it's like, hey, we found a bad problem with authentication for a device. Let's use Shodan to figure out how many devices there are that are internet connected, and then that becomes very scary. So, yeah, I think that's kind of the root of like with certificate authorities. If you use a really good, let's say RSA 4096 key in your certificate authority, that hopefully is something that, as long as it never leaves your company's IP, should never be compromised. Fingers crossed, and leave your authentication method much more secure than something that could potentially be brute force attacked through some sort of botnet, right? So, all right, thank you everyone for your time. I appreciate everyone showing up. Yeah. Thank you.
Oh. Would you be interested in presenting a version of this talk at one of our events?
Absolutely.
Haze 2, 3. Kind of works. Guess that should work. That's good. Okay. Okay, I guess we can get started. Welcome to my talk about Bluetooth on embedded systems deep dive. I'm Marcel Ziswiller. I joined Toradex in 2011. I'm gonna leave this June. I spearheaded the embedded Linux adoption by introducing upstream first, and at times we were top 10 U-boot and Linux kernel ARMSOC contributors. We have an industrial embedded Linux platform. It's called Horizon, and it's fully based on mainline technology. Mainline U-boot, distribute, KMS, DRM graphics, and over-the-air update with OS3. And the application layer is containerized with Docker or Podman. What am I covering today? I'm going to introduce Bluetooth. We're going to have a look at the specification. I also quickly talk about security. Then I'm going to compare a little bit the low energy with the classic. And then we have a look at the Bluetooth stack, also the BlueC, which is the mostly used Linux Bluetooth stack. Then I'm going to look at some of the Linux kernel Bluetooth controller drivers that are upstream, also how that can now be integrated if you have an embedded Linux system. And then we look a little bit at audio, because that is one of the main use cases with Bluetooth, not with BlueALSA, which is kind of a lean solution, mostly used in embedded devices, but I also quickly gonna have a look how that works on a cutting edge distribution nowadays, like this Silver Blue stuff I'm running here, for example. And then also I talk a little bit about Bluetooth debugging. If you have an embedded system where you have some Bluetooth problems, how you might address that. And I will finish it with a live demo here, okay? So Bluetooth, it's a short range, low cost, easy to use technology. It basically was invented to replace cables, not? So nobody expected it, but the 3.5 millimeter headphone thing actually did disappear, not? There was outcry at the beginning, but it's gone basically, not? And it operates within the unlicensed industrial scientific medical in the ISM band in 2.4 gigahertz. And with that, it of course has also danger of interference. Also Wi-Fi is there, for example, or other interference stuff are microwave ovens, things like that. Not. That's why it uses frequency hopping spread spectrum. So it usually performs 1,600 hops per second, so it jumps around in the 2.4 gigahertz. And with later specifications, it does that in an adaptive way, so it basically avoids any kind of interference stuff in this hopping sequence. So it can hop basically around in the 2.4 gigahertz. That is not congested in any way. Not. And packets are transmitted in, data is transmitted in packets, and basically each packet is transmitted in one of the 79 channels that the 2.4 gigahertz is divided in. And then each channel usually has a 1 megahertz bandwidth, and it uses Gaussian frequency shift keying modulation in basic rate mode. There are also other modes in Bluetooth 2.0 plus EDR, so it was an optional part, the EDR, the enhanced data rate. They introduced differential quadrature phase shift keying, which allows in EDR2 mode to have 2 megabit per second, and it uses 8 DPSK in EDR3 mode, which allows 3 megabit per second. And chips are usually fabricated in RF CMOS technology. Then, like I said, it's a standard wire replacement protocol. We also, it's low power. We see here in the table, there are Bluetooth classes and how many milliwatts, and that translated to dBm that they're allowed to actually use. Not. And it allows for ad hoc connection, voice or data transfer, and it's a wireless personal area network standard, basically. That means it's really confined to around the person. It's not really meant to go hundreds of meters. At least the original standard was like that. But of course, the range depends heavily on multiple factors, like whether you have anything that is blocking it. Also, we saw there are different modes, speed modes, so it also depends on that, of course, and also on the protocol class, whether classic or low energy, and then the Bluetooth class, meaning the transmit power that can be used, and of course also on the other end, the sensitivity of the receiver, and at the end also, of course, antenna technology, how they are aligned to each other, and all this kind of RF stuff. Quick history. So initiated, it was in 1989 by Ericsson Mobile up in Sweden, in Lund. And they basically, the real principal development on it started in 94. And by 97, they had a somewhat workable solution. And then what happened was that IBM was also looking for some technology to integrate into their ThinkPads to allow them to communicate. However, back then it was deemed too power hungry to really integrate the kind of the long distance, whatever technology into a notebook. So they somehow agreed to integrate this short link technology. So you would just hop from the notebook via mobile, go get your internet connection, something like that. At that time, neither IBM nor Ericsson was really a market leader in this kind of technology. That's why they agreed to make this short link technology an open standard, and that's how it basically came along. And then, so Ericsson contributed this technology they were working on, the short link, and IBM contributed some of their patents they had more in the link layer, around the link layer. And they knew that that will only work if they can recruit some more kind of technology companies. So they recruited Intel, which then in turn also got Toshiba and Nokia to join. So in '98, the Bluetooth SIG was basically founded, the Standard Interest Group, and they launched with 5 members at the beginning, Ericsson, IBM, Intel, Nokia, and Toshiba. And then in '89, the first devices were coming to market, and they, with a mobile headset, they earned the best of show at the Comdex. And the first mobile phone that had Bluetooth technology was the T36, and then the T39 made it to store shelves in 2001. And the name Bluetooth was actually only kind of a code name, but yeah, I would say, as usual, marketing kind of failed to come up with something better, so they just went with that. And kind of interesting, in 2012, the Chap Hartson from Ericsson actually got the European Patent Office Inventor Award for his work that they did at that time. So the Bluetooth Special Interest Group, that is really the non-profit, non-stock that stands behind the standard. Nowadays, we saw they start with 5 companies. There are more than 35,000 member companies. So it's very used everywhere. They oversee the development of the specification. Usually every year or other year they refresh it, so it's quite active still. And they also manage the qualification program and protect trademarks, and they meanwhile have a full network of applicable patents around this technology. And by becoming a member, you basically can license that to qualifying devices. I will not go through all the specifications here. The early ones were not really interoperable. All the later ones, they are quite keen that they stay interoperable, the devices. I mean, kind of backward compatible, of course. One interesting thing is, like I a little bit mentioned, Bluetooth 2.0, that was when multiple data rate modes got introduced. Then in Bluetooth 4.0, they introduced, actually under kind of marketing name Bluetooth Smart, they launched the low energy stuff. And the latest one that came out last year, it's now Bluetooth 5.4. Okay. A quick word about security. Of course, I mean, Bluetooth, the advantage is it's rather short range, so you cannot exploit it over high or big distances. And as such, it's deemed fairly secure. However, especially older devices, and remember, it's kind of backward compatible, and if you would still use some of the older early spec stuff, that is really deemed not very secure. Especially the whole pairing sequence is kind of easily to interfere with and exploit. A lot of this got addressed in Bluetooth 2.1, and also, of course, and that is also what most, for example, mobiles do. You kind of, you don't always are discoverable and all this kind of stuff, or even disable it if you don't use it. That way, it cannot be exploited. However, even the latest versions still have some kind of security problems. For example, you could easily do a denial of service attack with some kind of pairing requests, things like that. So if somebody would want to exactly now pair something, you could basically easily DDoS that. Then two attacks that also got kind of named is blue snarfing. That is when you would use Bluetooth connection to steal information, or blue jacking. That is when you would send some kind of unsolicited stuff to some devices. That was at times also quite a popular thing. And even last year, end of last year actually, it's fairly recent, there were some new unpatched vulnerabilities discovered, and that's even in the low energy part, and this is up to now, like I said, unpatched. So Bluetooth really has basically some security problems, but yeah, as it's only used in this short range stuff, I guess it's not that bad. Then BLE versus Classic, so it was introduced in Spec 4. It's basically a new incompatible stack, and it is meant for very low power consumption. It uses 40 channels of 2 megahertz rather than the 79 1 megahertz ones in the original spec. It increased the CRC to 24-bit rather than 8 or 16. And it can now handle unlimited devices, while before it was limited to 7 active slaves. It is lower cost, otherwise maintaining similar communication range. And initially they had a 500 kilobit per second mode. Later 5 spec also introduced a 2 megabit per second mode. And there are now dual mode or single mode implementations. So you could basically, usually the host side is usually dual capable, I mean, a mobile phone usually can talk to classic, older stuff or low energy, while there are certain devices that, for example, in the smart home or something like that only support the low energy spec. And for that, there is also a very lightweight link layer that can really provide ultra low power idle mode. That way you could have devices with coin cell battery that run multiple years. Of course, it depends at the end how many minutes or hours or whatever you actually really transfer data. Then the Bluetooth protocol stack. So we have a link manager that is for establishing the connection between devices. It authenticates the link and configures it. And also allows management stuff. And then it is using the services from the link controller. And supported services there are, of course, data transmission and reception. Also that there is a concept that you have a name, so you can discover stuff. You can request the address of the link partner, and then, like I said, the connection, authentication, and the mode negotiation. And then the host controller interface, HCI, that is basically the command interface in between the controller and the host. Then the logical link control and adaptation protocol, L2CAP, that multiplexes basically multiple logical connections, and it can segment and reassemble the on-the-air package. The basic mode payload is up to 64 kilobyte, and there is like a 672 byte default MTU, and there is a 48 byte minimum. Then there are retransmission and flow control modes, so it allows for isochronous data or reliable data with retransmission and CRCs. Then later specs also introduced enhanced retransmission mode, ERTM, and they provide reliable L2CAP channels. A streaming mode that's basically without retransmission. So that paired then with flow control allows unreliable channels, and the reliability is optional also in the lower layer with BDR or EDR interface. And what is special, so the number of retransmission and the flush timeout, so basically how long it waits doing this kind of retransmission, that is all configurable. And then there's also Service Discovery Protocol, SDP, so that allows to discover services offered by devices. And of course, the parameters that are behind what is offered. One interesting thing is the so-called radio frequency communications, RFCOM. It's basically a pure cable replacement of the RS-232 serial port. And especially at the beginning, a lot of devices were that way. You could easily convert something that used to use a regular cable serial port, you could convert it to Bluetooth. Then some other protocols is, for example, the network encapsulation, BNEP. That is basically, it just transfers data on top of an L2 cap channel. Main purpose is usually IP packet transmission. Then there are audio and video control transport protocol. That's used as a remote control profile, basically to carry commands from audio-video kind of devices over an L2 cap channel. And of course, you can also transfer the audio or video data. That is the AVD-TP. That allows, for example, the advanced audio distribution, the A2DP profile, to stream music in good quality, basically, over a L2 cap channel. Then one other one that never really took off, it's more or less historic, is the telephonic control protocol. That was more or less some of this initial thing, but nowadays nobody ever really adopted that. Then there are also a lot of protocols from other standardization that basically got adopted and are used with Bluetooth. For example, PPP, or like I said before, with BNEP, that you have TCP/IP or UDP stuff. There is the older from IRDA, from the infrared times, not the OBEX, Object Exchange, or even the wireless application environment, wireless application protocols, WAE or WAP. So how does that look in Linux? In Linux, we have BlueC since 2006. In the older times, there was even from Nokia some kind of a stack, but that was never used anymore since 2005 around. BlueC itself originated within Qualcomm. One interesting thing to note is that nowadays Android doesn't use BlueC anymore. They actually rely on Fluoride, which was formerly called Blue Droid. And that is a different stack that was developed by Broadcom. And the stack has user-space daemon and utilities around it. And also in the Linux kernel, there is Bluetooth subsystem. You find that in net Bluetooth. And it also has accompanying drivers. Those are to be found on the drivers Bluetooth. And kernel supports that since version 2.6. So let's have a look at the controller drivers. There are various interface protocols supported. There is, for example, the HCI via SDIO. Then there is HCI via UART. There are various incarnations, so many companies, Broadcom. There are also so-called H4 or H5 variants, while the H4 is kind of a regular 4-wire UART, so RxTX and RTS-CTS. There is also a variant called H5, which is a 3-wire variant. So you could basically come along with one less signal. There is also a low-level spec that was mainly used for Texas Instruments chips. Then Intel, Marvell, Qualcomm, Atheros, and also Realtek have their own incarnations of the UART1. Then also USBs is quite frequently used, not also the USB one. There are incarnations kind of from the various companies, Broadcom, MediaTek, or Realtek. Then there is a special driver for Marvell Bluetooth stuff, which has also an SDIO variant. This supports, for example, all these nowadays NXP chips, which we also use in some of our modules, not, for example, the 8997. There is a similar SDIO one for MediaTek chips. MediaTek also has their own HCI UART driver. There is a Qualcomm one for SMD kind of interfacing. And there is a new NXP one, which we actually now also migrated to. It's called BT NXP UART. There are also a bunch of obsolete ones. I was just curious, had a look at the Kconfig stuff, what is lingering around. I will not go through that, but this is some historical things, like some of the old Nokia mobiles had some special H4 Plus mode and so forth. And of course, various of these early Bluetooth companies changed hands meanwhile. For example, Red Pine, I remember we also used at the beginning when I was at Toradex, that meanwhile went to Silicon Labs. So let's have a look what vendors even have upstream support and how does that all kind of look like. Remember, I was evaluating for some of our later system designs all these various options. So, for example, Broadcom, they actually don't really market any stuff on their own anymore. They sold it off multiple times to, I wrote that here actually. So Infineon, formerly Cypress, is one that got some of their stuff, and also Synaptics later bought some of Broadcom's Bluetooth or Wi-Fi Bluetooth technology. I'm not really going to cover any of the Wi-Fi part here. For at least Wi-Fi 6 or 6E, I also talked about once in Austin. You can find that talk online, I guess. So Broadcom, the newer ones, they support Bluetooth 5.3 or 5.4 via UART as well. And for my testing, I usually used M.2 2230 form factor kind of cards, not. The Linux driver for that is the BTBCM, and the config also BTBCM. And you also need firmware for most Bluetooth, also Wi-Fi stuff. You will need firmware that then actually runs on this device, not which, of course, the firmware part is not really open source in that sense, which is one of the little troublesome pieces here. If in open source we find some kind of issues, you will have to kind of convince one of these companies to actually go figure out what in their firmware is wrong and whether or not they might fix that not. In the black terminal box, I have how it looks when you load that kind of stuff, and also with HCI config what kind of information you get. Another driver is the Intel one. It's actually very frequently used. Up to a few years ago, that was more or less the de facto thing you had in a notebook. Unfortunately, on the Wi-Fi side, it's a little bit different because they don't really allow that you could do anything with an access point mode. But that we're not really going to talk about here. The Bluetooth part is fairly mature, of course. The driver is BT Intel config and also firmware required. And again, how that looks when you load that. Then another upstream contender is MediaTek. There is the Philogic 330 or 360 with Wi-Fi 6 or 7 functionality. But here we talk about Bluetooth. It has 5.2 or even dual 5.4 support. Unfortunately, that later Philogic 360 is still very, very new. And there is very little known about it, and I have not had this one in my own hands yet. But the MT7922 I tested extensively, and that use BT-MTK driver, and again, how that looks when you load it. Then another one, NXP, which I'm also going to use in the demo. It's, for example, on the Verdin AM62. This is the top module shown here, the little Wi-Fi module there. It's the IW416, which is kind of a new thing from NXP, but it uses older technology. So it's more or less exactly what a lot of us embedded Linux or IoT kind of users are using. It supports Bluetooth 5.3 via UART. Then the upper one, this is kind of a proprietary footprint. It's called MuBlox Maya. And the lower one uses an M.2 1216. The Linux driver, like I said, the newer one is BT-NXP UART with the config, also BT-NXP UART. And you can use it with either separate firmware, so UART IW416, or with the combined firmware. I will talk about that also a little bit later. Then another one is Qualcomm. Qualcomm has, of course, also a wide range of devices supporting Bluetooth 5.3 or the latest one 5.4 as well. It's the BT QCA driver, and they call the firmware stuff, actually they call it RAM patch. And that's how it looks when you load the Qualcomm one. Then last but not least, Realtek also has interesting chips that support this technology. For example, the RTL8852CE or later RTL8952. Again, that later one is rather new, not too much known yet about it. It's the BT-RTL driver with accompanying config and the firmwares for it. Let's have a look how that can look on the integration side if you have an embedded Linux system. This is an excerpt from one of our schematics with this Maya IW416 based one. So on one hand, of course, you have the Bluetooth interface. Here it could be SDIO. Actually, here if SDIO is used, you could also have it shared, so-called multifunction. So you would really use the same interface for Wi-Fi and Bluetooth, which in our kind of experience, that of course can also cause some problems. And you can also use UART. As I mentioned earlier, usually it's RxTX and RTS-CTS. Quickly going back to the schematic, that would be on the right-hand side upper corner, not. While on the left side, it's the SDIO, which actually is used for Wi-Fi. Then USB would be another way to connect. I talked about that last year in Prague, so if you're interested about how to do USB on embedded Linux, that talk you can also find online. Then also there is the PCM stuff for audio available. However, while that is used heavily on, for example, mobile phones, and they really do it mostly, for example, to save more power, this cannot easily be used usually with embedded Linux, as you would require a special firmware that would even support that. At least in the NXP case, this is how it is, and so far I don't know of any customer that would have succeeded to actually pull that off. I mean, you would need a really big project and convincing NXP to provide you that firmware node. Then another thing are, of course, the control signals. Usually you have some control signals for power. For example, the PD, power down signal, that is connected, usually to a GPIO node. There might be reset signals. In our case here, the BT reset and WLAN reset would even be separate, but it wasn't used in our design because we were just controlling the power to it, and it has a power on reset, then you don't really need separate resets. However, I will show later that this also causes some kind of issues. Another kind of signal would be for strapping. So you can tell the module which interface it even uses, and especially also there is some kind of a boot ROM also on the device where it expects the firmware from. Then usually there are wake signals, and those usually go in both directions, so that the host can wake the device or the device can wake the host. Other kind of signals is for coexistence stuff. That would allow, if you have also like an LTE thing on your system, that you could actually make sure that they don't contend for some frequencies and airtime. How does that now translate to the device tree? So this is the upstream kernel org device tree for the word in AIM62. Actually, this is only the part, the DTSI, that is relevant for the Wi-Fi SKU. Of course, we have SKUs with or without that assembled, so different ones then apply. So you see here, like I said, for the power, there is a power sequencing thing. It uses this MMC PowerSec Simple driver. And we basically, even though this is the Wi-Fi enabled power signal, it uses, that's just because that driver calls it a reset. But as we have seen in the schematic, we're not really connecting that to reset, but rather to the power side. And then it does a power on reset automatically. Then, while I'm not going to really talk about Wi-Fi today, this is the SDHCI part, so the SDIO. We also see here, that is where you hook up this PowerSec stuff. And then for Bluetooth, it's using the UART. You can see here that you usually specify that it has RTS, CTS, so it knows that it has to use the UART in this 4-wire mode, not with RxTS, RTS, CTS. And usually you have a separate Bluetooth node where here, that's the compatible that is actually applicable for the IW416 for the BT NXP UART driver. And like I said earlier, this is just basically a refresh of an old chipset. That's why it uses the 8987 compatible here. I mean, it's quite common in Linux that you don't introduce new compatibles for every new thing if it's just still compatible. And one special thing that is a difference to the old 8987 here is that it starts immediately by default with the 3 megabaud, while the original 8987, I think, started in 115 kilobaud, and then you had to do this nasty switching, which also caused a lot of problems. Then, like I said, one thing where SDIO also is relevant is for the firmware loading. So you could have dedicated firmware. So you would basically Bluetooth and Wi-Fi would load each their separate firmware. However, the way we now wired it, when we don't have separate resets, that doesn't really make fully sense because you cannot really kind of start over separately with either Bluetooth or Wi-Fi. You always will anyway have to power up the whole thing and everything starts again. That's why usually it makes more sense to use the combined combo firmware. And also this has the advantage that you can use the faster interface, basically SDIO, to load the entire firmware block node. However, we discovered that that can cause an issue in the load order. So if the UART driver would load, the UART module would load first, it of course would kind of expect the firmware to be there, respectively try to then load its own firmware. But if you want the combo firmware, that's not what you want. And this can be worked around just via mode probe stuff. This is how we usually do that on our systems. And that way you avoid this problem. Then let's have a look also at the audio stuff, because that is a fairly common use case. So Blue ALSA is basically the rebirth of the BlueC and ALSA integration. So in the older BlueC versions, before 5, that was basically part of regular BlueC. They then dropped that in favor of third-party applications that do this audio integration, and that's Blue ALSA is basically one of these third-party ones. And of course, on the distro side, they usually use a more full-blown solution. But for embedded devices, this is a very lean middleware between the audio application and the Bluetooth audio profile for such devices. And it's, like I said, status quo alternative for like embedded stuff. And it supports the same Bluetooth audio profile as a full-blown solution. It also has much fewer dependencies, which is, of course, usually makes life easier for your embedded system design. And it's also acting at a lower level in the software stack. And it does register all the known Bluetooth audio profiles with BlueC, and in theory, so it should all devices that are out there with audio capability should be able to connect to that. This is how it looks like. So they have their own Blue ALSA daemon, which also talks to the regular Bluetooth daemon, which also talks then to the device. And it supports these various profiles. It would also support ALSA MIDI stuff, which for certain devices is still widely used. So it's, like I said, especially for an embedded system, and it allows audio streaming, and otherwise it, of course, is constrained to the regular ALSA IPA, as it's not using any kind of more fancier option. The Blue ALSA daemon is the heart of it, and it handles the whole connection and configuration, everything. And also, of course, under the hood, it's using dbus, just like the regular Bluetooth stuff also. And the way it does that is with so-called ALSA plugins, which hide all the dbus specifics, and that allows that you can use regular PCM, mixer stuff, for example, as with other ALSA stuff, and also seamless MIDI handling. So the daemon registers org Blue ALSA on the dbus and then handles the pairing, connection, and using of the device. It relies on the regular high-level Bluetooth pairing and connection procedure that the Bluetooth control, for example, allows you to do. And the plugins, they create virtual ALSA PCM devices, and they can be used by any application that knows how to do PCM device stuff. It's basically a PCM I/O plugin. However, it doesn't associate a sound card with it, and that you will also see that it doesn't have a kernel proc interface for it. So it's a purely virtual thing. It's a software thing. But it does allow playback and capture with the -D device Blue ALSA. So that means it's using the Blue ALSA plugin thing. And it also allows A2DP, high quality audio, or HSP, HFP profiles via SCO links for like phone type connection. However, Blue ALSA itself doesn't do any of the call feature integration that you can optionally do via Ophono. So you can, when you compile it, you can specify, or when you do it with Yocto, you can have, you can also specify that. Then the more full-blown would be Pipewire. I'm running out of time, so I'm not going to talk about these details more here. But Pipewire and Wire Plumber, that's basically how that all works in a full-blown distribution. If you want to do that on an embedded system, it's also possible. So here, how you would build something with the Yocto project that uses the full-blown stuff. And make sure to, basically, when you have multiple such third-party audio applications, they will content, so you have to also remove the Blue ALSA if you want to do full-blown Wire Plumber, Pipewire stuff. Okay, and then another thing is some of these basically codecs that are used with especially high-end audio, they have some licensing things which you might want to have a look at, which, for example, here you can just say accept license flag commercial, then it would build it with all these codecs. I just didn't want to mess with whether it would not work or something like that. But of course, for a real device, you would have to make sure that you know what you're doing with the licensing. Then a quick word on debugging. Make sure to find a good reproduction scenario. That is one thing. So with automated testing or scripting or something. And then it's mainly about figuring out where in the stack your problems are. On the low level, firmware, hardware, you can usually check either the UART or USB or whatever communication you are using with a logic or protocol analyzer. And then don't forget also to have a look at the control signals. Sometimes we have seen some glitching on those control signals can also cause problems. And then one can analyze the actual HCI communication, and that can be done using BTMon, and this is a tool that is available in the Blue Sea user space stuff, and that one a little bit inconvenient thing, it writes not only to a file but also to standard out, so it's really hard to kind of pipe that in a way that you could live run that then to a Wireshark or something like that on your host. While for example, with USB Mon, that is possible to do, but I have not figured out with Bluetooth that cannot be easily done. So usually I just trace it to the device and then just copy the file back, and you have to do basically, you can't do runtime analysis, you have to do it afterwards. But Wireshark allows to visualize it. Here I show a Wireshark session. On the top you can see it shows you where the communication comes from the host or the controller, and you can just like usually with a Wireshark you can look at what exact data you have and what exactly it's doing. In the lower compare windows, I have the RX and TX that were captured on the actual UART, even lower level than HCI. So without even knowing what it is, it's just the bytes that are transferred on the UART, for example. That way we were able to figure out whether the problem is some kind of corruption just on the bytes on the UART. Very good. Then let's have a look at the demo. Here I show what parts are used. Actually, I'm not going to use the Shelly because that stupid thing emptied its coin cell battery. And I heard some rumors that's probably because it runs an old firmware version. They fixed that meanwhile, but updating that firmware is not entirely trivial. But when I'm back home, I will try that, of course. So I will use the lower one. It's just some like $1 kind of Bluetooth audio receiver board that I once got off AliExpress. And then I pair it with our carrier board. It's a Dahlia with a AM62 SOM. Or you can do the same also, for example, with either the MX8M+. I just see that I have a typo there. I will fix that and upload slides for that. Then let me switch to that. Actually, for that, I quickly change here to mirror mode, otherwise it is kind of very inconvenient. Okay. So that would be that. Can you all see it? So that is the wrong one. Why did it not go to mirror mode? Now, so that would be, so this is the window where you see the UART, and this is my notes. I think this should do it. So let's fire it up. Then I also have here this other hardware. I will plug that in. So that is blinking away. And we are booting here. So I can log in. We can have a look. It's now down. Remember RF kill. So it's blocking it by default. I'm going to unblock the Bluetooth. Let's have a look. Now it should be running. So it's up and running. And you see it's Bluetooth version 5.3 that it's running here, not. Then we can go to Bluetooth control. and we can basically scan. I'm curious, probably there are so many Bluetooth devices here. Let's see whether that will work. So, yeah, that, as we kind of expect, plenty of things that when you do a scan, it sees lots of stuff, not? And this HWBT, yeah, it already went on again. I could, of course, scan off. Oops. Anyway. It is this BTHW1. I do know its address, so I now paired it. I can connect to it. And then let's exit this thing. And like I said, so you can, with Blue also, you can have a look, and it using the A to DP in SBC mode. And we can, of course, then also play some music, either with regular A-play, for example, you specify, like I said, this -D device Blue also, and you can use it just like any other PCM device, not? Or you can use speaker test or whatever thing, not? Okay, that was basically it. And let me see. Are there any questions? I also copied the whole demo stuff that you can see what it would be doing. Questions, anybody? I know I run more or less out of time. Probably that would be it. If you have any questions, we can also discuss it outside. Thank you very much. So. Thank you. A little bit too long. Huh?
Hi, am I audible? All right. Hey, thanks everyone for attending the talk. I know this is the last talk of the day, but thanks for your patience. We are going to talk about standardizing the generation of images and signing of the boot images with U-boot kind of as an example. Let's quickly jump to it I'm Vignesh. I'm working for Texas Instruments for the past 10 years, working mostly on Linux K3 generation of SoCs, supporting Linux and U-boot. This is Neha.
Yeah, hi, I'm Neha, and I'm also working in Texas Instruments for the past 2 years, and I mainly work on U-boot development.
Yeah, so we also have Simon Glass, was not attending the event, but we work closely with Simon in terms of getting the boot images for the slightly weird K3 architecture to be an upstream in a consistent way. So, just talking about the motivation for the talk, bootloaders of modern SoCs have do a lot more than just initializing the DDR and loading the kernel, right? So there are multiple platform level firmwares, and they require quite a bit of complex packaging and signing procedures, and U-Boot has solved this in different ways over the years, and this is one of the standardization efforts that U-Boot went through, and how you could kind of leverage this across the SoC ecosystems, right? So we'll provide a quick overview of U-Boot and the firmware packing problems, and with an example of a boot flow of a complex SoC, and how we can leverage the binman tool and U-Boot in terms of firmware packing and extending the bind, and how we extended the binman to support TI-K3 class of SoC, and the future developments around it. Okay, so let's get started. I guess most of you may have already worked on U-Boot here, so it's just an FYI that it's U-Boot as universal bootloader. It has a rich set of peripheral stack, and it's very flexible. It's kind of tightly integrated to boot kernel, Linux kernel, and it supports multiple architectures, ARM, x86, the RISC-V recent ones, and there is device tree-based hardware description support, and any other means of describing the hardware, and yeah, so it's one of the most versatile bootloaders available. So let's start with the problem at hand, right? So long ago, if you were working with an MCU kind of a device, it's mostly a U-Boot that is a bootloader that you would have, and just flash it into the flash memory storage that's there, and build the image with make, flash it onto the flash storage, and you're done, and basically some amount of environment to do the selections, right? So and moving on, if you were to look at the very simple microprocessor class of SoCs, we will at least have something called as U-Boot kind of provides you something called as secondary program loader, which would be a first set of program that gets loaded, which would do the DDR initialization and load the full set of U-Boot bootloader with command line interface and whatnot that allows you to load kernel from different storage medias, right? So there's also a support for something called tertiary program loader, which could be a precursor to SPL, and it would open up a larger memory within the SoC, or help us choose between different boot medias where the SPL is located, and kind of initialize that. So now, as you can see, there are multiple components that are getting added up here. So a trivial way is to just cat them and create a big image and go and flash it into the storage media. But there is always a need for metadata to be there along with these images, which is at what offset would you flash them at, how would you pad them, align them, and whatnot. So and of course, there may be additional firmwares that we'll talk about, and which makes the image to keep growing and growing with different components. Now let's look at an example of modern systems, right? Starting with, let's say, x86, right? So even there you have an SPL here, U-Boot, but there are a bunch of vendor-specific microcode-related firmwares and whatnot. So all this would need to be packed in a certain way, flashed at certain offsets in a certain manner, and all this essentially requires some amount of intelligent packaging tools, right? So if you were to look at ARM64 examples, a typical SoC would maybe start off an SPL, and this is an example, or just an example. It need not be exactly same, but a typical SoC would start off ROM, RAM would start off an SPL, and there is something called as a secure firmware at EL3 level, another one, and a secure EL1 level, and then the U-Boot that is running has a non-secure firmware, and which then boots up to Linux, right? So, and if we were to look at the load sequence, this is probably the example how the control would flow, but if you were to look at the sequence of how the image would load, you probably don't want to duplicate the boot media drivers and multiple software components, or probably use SPL with one image that can load multiple. I mean, SPL would load all the images, like the EL3 firmware, the EL1 level firmware, the U-boot at the non-secure EL1 level, and so on. So, right. So, let's look at what we call as an heterogeneous SoC, which would have more than just an application Cortex-A core, right? So there may be multiple real-time cores and whatnot, right? So in such a case, it's now even more. There probably is a ROM running on one of the MCU cores that would start off an SPL, and then SPL is responsible for loading multiple of such firmwares, right? The examples that we saw on the previous slide, additional to that, there may be an AUTOS running on the MCU core. There's power management firmware that would run on a power management or a dedicated core that's meant for power management. And ROM may additionally load a security management firmware, or it may again be an SPL that is doing it, right? So, yeah. So we'll take a subset of the problem and try to see how the image would look like, or what it entails, right? So if you were to just look at what is required for an ARM64 system to kind of boot up and run, right? So you have the EL3 level firmware and the secure firmware, and the power management firmware, and something that will run on the non-secure EL1 side, which eventually would take you to Linux. So yeah, so we'll just take a subset of this and try to look how the image for such an image would then be needed to be loaded by SPL stage. Okay. So. So this is something similar what we have on our K3 generation of devices, where the first core or the primary boot core is a MCU core, which is an R5 core, and then the R5 core runs an SPL image, which would then start off the application core or the big A cores, A72s, A53s, and so on, right? So, so there may be multiple MPU cores and a single MPU core on the same die, and we need to basically start off all of them. So this kind of diagram shows the boot flow sequence. So the ROM would start off an SPL on the R5 core, which is kind of in a different color here, and this SPL is responsible for loading the rest of the system images. So let's look at the image itself, right? So as the TFA, or the trusted firmware ARM, is the image at EL3 level. There will be an optional opti add secure EL and EL1, the secure OS. And there is a device management firmware, which we call DM in the TI context, but it's essentially the system control coprocessor that ARM defines, right? So all this essentially combined with the SPL that would run on the application core and the device tree make up a binary that would be required to get the A core started up, right? So I think the easiest way that you would start packing this up is something called as flattened U image tree. If you have worked with U-boot, you could be familiar with this, which essentially is a device tree-like description language for images. You would describe images using a device tree-like syntax, and there's a tool called mkimage within the U-boot, which will help you to essentially take this and pack them up with basic offsets and alignments and so on, right? So taking the problem a bit further, what we also need to do is add security on authenticated boot on top of it, which essentially means that each of the components here would need to have a certificate that is signed by both SoC vendor and maybe countersigned by the end user as well, right? So with an optional encryption requirement as well, and you would be signing using some sort of public key cryptographic methods such as RSA or ECDSA. So as you can see, it's probably that the entire image is signed with a single certificate, or each of the component may be signed with their own individual certificates, requiring additional data that is provided for each of the components, right? So, and again, it's not just a matter of packing. You'll also have to sign and provide ability for customers to use those scripts and sign on their own as well, right? So this container on the right essentially is what we call in our TI boot flow TI SPL.bin, but it's essentially a combination of these images that get started on application core. Okay, so how did we have it like maybe up to a year ago when you had, we were essentially having a bunch of custom scripts which pack the images using the makefile and the mkimage tool that's available when you boot. So take all this inputs and feed it into U-boot repository, has command line arguments to the makefile, and you basically, the U-boot build system would give out TI-SPL.bin with all this included. But then there was a separate set of scripts that TI used to maintain over at a different Git repository called cosecdev K3, with which vendor-specific custom scripts used to be. It's basically a vendor-specific scripts which will help you to sign each of these components and create the final image, right? So as you can see, it's kind of has its own sets of issues. First of all, it's kind of is not scalable because each end user may be coming from a different background and they need to learn vendor-specific signing scripts, which is itself in a painful process. It's kind of not distro build friendly, wherein we are now forcing the distro creators to pull in certain SOC-specific scripts just to create those images out. And within the boot itself, there are variations in terms of whether or not you want to start and load an MCU core or not, or whether the device follows a non-secure boot flow versus a fully secure boot flow, or the high secure device flow, or whether the end user has all this complexities to be handled within scripts, and means that you need to understand the scripts in and out to do any changes that you want to do. Of course, all this did not have any unit level testings, which meant that it's very easy to have it broken. So this kind of is a snapshot of how the script kind of looked, and I'm not going to go into details, but it essentially shows you that it's pretty much not straightforward to read it intuitively and understand what it's doing, right? So I'll hand over to Neha to show how we went through this and actually solved the problem using the binman flow.
Am I audible? Yeah, okay. So whatever Vignesh has described up to now is a subset of the number of challenges that we see when we actually pack firmware. For example, in embedded systems, you'll need to make sure alignment is proper. You'll need to make sure that during your build, the dependencies that you need that finally get stitched up into your final bootloader binary have to be present before you actually go and pack it. At the same time, there is also a need for runtime discovery of content. Stuff such as compression. Compression is very important in when it comes to packing bootloader binaries. Formats, standard formats such as FIT, CBFS, FIP, all of these are again just headers that you have prepended on top of your bootloader binaries. These are problems that are solved individually by SOC-specific tools with SOC-specific scripts. And whether or not you'll actually be able to examine an image finally. All of these are challenges that you come across when you pack bootloader binaries. So Simon Glass had initially developed a tool called binman to solve these issues. So the same way that we describe hardware in the form of device tree, you can actually reimagine the bootloader image as described data. So at the front end, what you'll have is a device tree which actually describes what goes into your final binary. and you have a Python backend, which is the Binman tool. And this is right now loosely coupled with the U-Boot project, but it is possible theoretically to move it out and use it as a standalone tool. So an example you can see down here. So what we've done is just packed a U-Boot SPL binary and a U-Boot binary with padding in between. And we've explicitly set the offset of the U-Boot binary to 8,000. So it's visually, you can see clearly what's exactly going into your final binary. And that is the beauty of the Binman tool. So when does this Binman tool run? As part of the U-Boot build system, it runs once all of the inputs that are needed for the final boot image. Once they're all built, Binman runs. And it can also be run later. For example, you have a signing server that you want to sign with different keys later on. You can even run Binman later on. And it's a standalone CLI utility, which you can, again, run at any time. So the crux of Binman, how it was built, is entirely based on entries. So each image actually consists of entries. Entries are nothing but data. So each entry, as you can see, like the U-Boot SPL entry and the U-Boot entry, they're just blobs of binary data. And you have the capacity to add properties to these entries to further manipulate the way you want to change up your final image. Entries will be packed one after the other, unless, for example, you specify an explicit offset, in which case it will get packed at that offset. And entries are hierarchical, so you can have a big section entry which consists of multiple child entries, and Binman is smart enough to work its way from inside out. So this is what it looks like. You have the base entry class and a few of the properties, like, for example, what offset the entry is supposed to be at, if it's aligned or not, the size of the entry, again, it's optional, and whether or not it's part of a larger section. So all of these are properties that go into your base entry class, from which you derive the entry blob class, which is, again, nothing but a binary blob. And this is the most commonly used entry, at least in Binman right now. See, for example, we have image-specific classes that have been derived from this blob entry, like U-Boot SPL and U-Boot image. Again, these are standard U-Boot images, so these are already existing. But to solve our problem at hand, we need to extend this to fit our use case. So how do you do that? It's very easy to add an entry in Binman. So all you need to do is just add a Python file with the extended entry class in the Binman entry type directory, and Binman will be able to find it if it's invoked in your device tree. So you can even have tools that run within your entry class. So all of the magic of signing and alignment and all of that can be abstracted out into this entry class. And the main logic is in control.py, which most chances are that you will not need to touch it right now. It's just, that's where the whole packing goes in, and it figures out what to build and when. So you can look at other entries for examples on how to add your own entry type. And again, another great aspect of Binman is that it has 100% code coverage. So if you add an entry, you have to add a test to make sure that it's covered. So this is what it looks like after we migrated to using Binman. So as you can see, there are no external repositories. There are no long shell scripts that actually go and do the common MK image stuff that you see. So all you have to do is give the inputs to U-Boot using Binman, and the Binman device tree specifying the way you want your image to be, and it will generate out the required tispl.bin. So this is what it finally looked like. So this is a snippet of the device tree that we used. So the complex tispl binary that Vignesh had mentioned before has been put into a very simple visual device tree format. So here you can see you have a TFA binary blob, which in our case, needed to be signed by an X509 certificate on the top. So that is your TI secure entry type on the top, which has properties like content, pointing to what it has to actually go ahead and sign, and the key file with which it has to sign the image. And then you have, again, an opti binary below it, again, doing the same thing, going ahead and signing the opti image. And since DM is not a standard image, what we did is we made it a DM blob ext, which is an external blob entry. So external blob entries are very useful because you can just go ahead and grab external binaries that you provide in the build. So it'll just go and search for tidm.bin, and once it finds it, it'll just go and pack it in the final image. And yeah, so this is just the continuation. So you have the A72 SPL binary. Again, it's the same thing that's being done. U-boot SPL node DTB is again is a standard entry type. So we've already have support in the binman directory for an SPL binary. Similarly, we have support for the device tree binary, which is packed at the end. So a few things to note here, which show how flexible this tool is. Again, what I've mentioned before, custom entry types such as TI secure, you can extend it to fit your use case. Binman is also able to evaluate config options. So for example, you need to use the same binman device tree across boards. They probably have this, which probably have the same SOC. You can do that by making use of kconfig. And standard entry types. So binman has been actively been worked on by the community. So you have support for numerous standard entry types, which make porting to using binman very simple. So putting out that slide once again, just to give a contrast of how it was versus how it is now. So yeah, it is in a much better shape. So again, a little sneak peek into the TI secure entry Python class. I'll just go through this really quick. So apart from the special init method, you have the read node method. So the read node method is what goes and grabs all of the properties from your device tree. So it uses FDT tools to go and get those extra properties that you've probably defined, again, to fit your use case. And you can use that later on in your entry. Now the meat of this whole binman entry is the obtain contents method, which actually goes and does whatever magic you've abstracted out. In our case, the get certificate is what goes and uses OpenSSL to generate that X509 certificate. So all of that has been abstracted out here. And obtain contents sets the contents of that entry to whatever you want it to be. Another important method would be the process contents. Say your blob includes symbols that have changed during build. Process contents runs again for every entry at the end of binman, the binman build, so that it goes and updates the data binary to fit those new symbols in. And another method is the add bin tools method. So bin tools is just a special way of saying that you can use other executables in the binman flow. And this really shows again, the flexibility of binman. So for example, in our case, OpenSSL was a tool that earlier shell scripts just invoked. But now, since it's a bin tool, which again goes and does the same thing, but you've abstracted that out. So we go and use that OpenSSL tool, and that is a bin tool already. So this shows how you can also extend to add bin tools. If your board currently generates boot binaries by running some scripts, chances are it's very easy to port them with the use of bin tools. So numerous advantages to using binman. One is, again, it's data driven. So it's very visually appealing to read and understand. And what happens is that this helps familiarity across the SOC vendors who will be using binman commonly. And again, more and more platforms are being migrated to Binman, so a new SOC developer will be able to ramp up much faster and will be able to port a new SOC much quicker than before. Also, it's object-oriented design, so you've abstracted much of the heavy labor out of the what it used to be, and it's all abstracted out. So that's another benefit. And there are functionalities that haven't been covered here, but are great, like for example, templating and fit generators. These all help in code reuse. So considering your again, your SOC will have numerous boards that it supports, you can reuse your Binman code across all of them. And runtime detection of symbols is again a really great thing. So in our case, we use a fit header to actually go and find the offsets. But in case you need symbols to figure out where you want to jump to at the end, Binman does that, adds symbols according to the image position. So that's also a great way of building your final image. A few things that we are currently developing. One is the ability to pass firmware via the CLI argument. So currently, all of the file names are hard-coded in the description. So that's something we're trying to get away from. And again, many boards are present in the tools directory. Many scripts are used for building different images, which all of them can be moved to Binman at the end. So that is, again, something that we are working on. And signing within a fit generator currently isn't supported, but that is also in active development. So I'll pause here for Q&A, and a few open discussion points that are currently being discussed both in person and on the mailing list are listed. So yeah, I think I'll open it for Q&A. I guess then, thank you.